Hello, everybody. Welcome to the annual Virtual Quantum Summit in Cisco. This is the first day of the 2 days event that we are very excited to show everybody what is Cisco is doing and what is the state of the art in industry and academia on quantum networking. So the first day is focused is the uncontrolled software and compiler platform for scaling out quantum computers. My name is Reza Nejavati, and I lead the quantum research team in Cisco. With this introduction, let's get on the first day agenda, which is I am very excited about it. So we're gonna kick a start our day with two keynotes, one from industry Cisco, from Vijoy, and then Daniel, an academic keynote speakers. After that, we swiftly move on, and Cisco research and engineering team will show a deep dive into Cisco compiler software features and give you a demo and let you know how you can use it. And after that, we go to a series of the industry and government invited talks, which is major industry players in this area, and also one speaker from DOE and a research center in Europe will set their vision and of their company and what they do in this area of the quantum computing compiler and software. And then we conclude our day with a panel. So with that introduction, I would like to introduce our first speaker. However, before I start, please be aware that there is a Slido. If you have registered, you get a password, and you can use it to type in your questions. We do our best to ask the question after talks or in the panel. So with that introduction, let's go to our first keynote speaker, which is Vijoy Pandey. Vijoy is the senior vice president in Cisco and general manager at Outchip by Cisco. He leads the Cisco internal incubation engine, which is focused on emerging technologies, and also he oversees the Cisco research, developer networks, and Cisco open source and responsible AI efforts. Under his guidance, Outchip pursued a lot of initiative in areas in AI, enable infrastructure, and quantum computing and networking. With that introduction, Vijoy, is over to you.
Well, thank you, Reza. Welcome, everyone, to Cisco's Quantum Summit. As Reza mentioned, we have an exciting set of speakers lined up. Plus, we have some really cool demos to show. I'm Vijoy. Like Reza mentioned, I run this group called Outshift. It's Cisco's internal incubation engine, looking at what's next and new for Cisco based on emerging tech. And we are going after adjacent markets that Cisco is already in. So think about networking, security, observability, collaboration, and think about personas that are adjacent to where we currently play, both user personas as well as buyer personas. A big part of my charter is also to look at what Cisco research comes up with, and Cisco Quantum Labs is a big part of Cisco research. And we are here today to talk all about quantum, which leads me to this slide, which is the two seminal problems that we as an industry have been working on for decades: superintelligence and quantum computing. And as an industry, we will continue to work on them for decades more to come. And just like in any field of scientific discovery and invention, there are paradigm shifts that happen every decade or so that move the ball forward dramatically in superintelligence as well as in quantum computing. So for the AI space, we just witnessed one such paradigm shift just about a couple of years ago through the ChatGPT moment. It's a transformer moment, but it's better to call it the ChatGPT moment. It doesn't mean that we have achieved superintelligence, but it does mean that the ball has moved forward enough that we can now accelerate aspects of all human work. So when are we going to see such a paradigm shift for quantum computing? When is the ChatGPT moment for quantum computing going to arrive? Where things may not be perfect, but the ball has moved forward enough that we can solve really, really hard problems and scalable problems. And of course, what is that paradigm shift? So when will we see that shift? And what is that paradigm shift? To answer the first question, which is when are we going to see that paradigm shift? I did a little bit of an exercise. I plotted the number of seminal breakthroughs in this field over the past few decades. And you see that in this chart here. And we see some distinct paradigm shifts over the past 30, 40, 50 years. Let's say centered around QKD, centered around Grover's and Shor's algorithms, centered around the first quantum gate, and so on and so forth. But whereas breakthroughs used to happen every few years, a few decades ago, you can see the uptick in the announcements taking place and the breakthroughs that are happening in the past couple of years. They have just accelerated exponentially. They seem to be happening almost monthly. Even if you normalize it for the social economy that we live in, they're still happening monthly, which is a pretty strong signal of a very simple message that a paradigm shift is imminent. So that answers the question, when is that paradigm shift going to happen? It's imminent. Then the next question is, what is that paradigm shift? So for that, let's take a look at what questions and the conversations that are taking place in this quantum computing space today. And what we see here, I'm not going to drain the slide, but what we see here is that quantum computing is moving from physics-based outcomes to systems-based, real, messy, business-oriented outcomes. The questions being asked are around investment protection. I'm buying multi-generations of these quantum computing nodes. Can I protect my investment? Multimodality, like can we not bet on a certain amount, a certain kind of technology that's going to win, but look at algorithms that are optimized for the right modality for the right job? Can we right size our infrastructure? Can we think about multi-tenancy, multi-vendor environments? Can we think about horizontally scaling computing and maximally utilizing what we have already and making sure that their entire data center is easily operable? So as you can see, all of these things are very real business-oriented, messy, brownfield kind of conversations that are taking place, which leads me to this slide again, which is, yes, we had the ChatGPT moment. We know that a paradigm shift for quantum computing is imminent. And what is it? To me, is the emergence of scale-out distributed quantum computing. Again, it's not going to be perfect, but it'll accelerate the solving of really hard problems at scale. And to me, this is something that we've actually been working on for a while, which is, why is it scale out and why is it so important? First of all, classical computing has a physics problem. That's why we are all here. And I love this quote by Feynman, which says, nature isn't classical, it's quantum. So why are we trying to solve it through classical means? And so classical computing has a physics problem. So we want to get towards quantum computing, but quantum computing has a scaling problem. And we know that we are at hundreds of qubits. Usable qubits are even lower. How do we get to pragmatic, practical, hundreds of thousands or millions of qubits where computing is possible at scale? And that's why we're all here working on this problem. And quantum networking, to me, is a solution to both of these problems. Both the classical problem, computing has a physics problem, as well as quantum computing having a scaling problem. Quantum networking is going to come in and solve for both of those. And quantum networking is actually here today. So at Cisco, as you can imagine, we are maniacally focused on building out the quantum internet. We are a quantum networking and quantum security company. We aspire to be that. And we want to start with building out a quantum data center network that actually connects discrete quantum computing systems and enables distributed quantum computing. So which means it's not just the networking hardware, but it's also the protocols, the software, and the applications that enable scale out quantum data centers. Then we would connect quantum data centers to quantum data centers, and finally connect those to quantum sensing devices to form the end-to-end quantum internet. But as we are building out this stack, this quantum internet, quantum networking stack, which is the hardware, the protocols, and the applications, we realize that the same quantum network can also solve some of the physics limitations in classical use cases and reduce or minimize some of the limitations going forward. So using that same quantum network, we can enable novel classical use cases as well. So because of these two use cases in the quantum domain, as well as in the classical domain, you will see us building this stack out comprehensively. We announced back in May, we announced the photon entanglement source chip. Today, we are announcing Cisco's quantum compiler. This is a network-aware distributed quantum computing compiler. And the Cisco team is actually going to walk you through a demo and details later in the day. But this compiler has a few industry firsts. It's the first network-aware compiler that we know of. It allows you to plan for and right-size your quantum data center. So it starts right from there. When you're thinking about creating a data center, planning for your data center, the step one, which is, can I right-size my data center? The quantum compiler is going to help you do that. Then it'll allow you to partition your quantum circuits in an optimized manner over potentially multiple modalities and multiple generations per modality so that you get investment protection. So the partitioning and optimal partitioning is what it does next. Then it allows you to schedule and run this partition circuit over this distributed environment. It allows for multiple tenants to operate on the same infrastructure, maximally driving benefit over that infrastructure, and it enables distributed error correction, which is also an industry first. All of this over a common set of protocols that will also be leveraged for some of the interesting classical use cases that we will talk about tomorrow. And that's the whole theme of tomorrow. And with that, I'm going to leave you with one of my favorite quotes from Thomas Kuhn, slightly paraphrased. A paradigm shift is largely a promise of success. Normal science consists in the actualization of that promise. We are at the precipice of a paradigm shift in quantum computing and walking towards scalable distributed quantum computing. It's time to run. Thank you. Back to you, Reza.
Thank you, Vijoy. We have one question. I picked one question, and because it's most frequently asked, is that when and how will Cisco start offering quantum networking to customer in practical way?
Yeah, so it's a great question, and I think the way we are thinking about this problem is there are still hard problems to be solved in this space, in the quantum networking space, and we're working on all of those. But as we work on those problems, both in the hardware and the software domains, currently we are signing up for design partners to look at specific use cases, both in the distributed quantum computing space as well as using the quantum network in the classical use cases space. We're signing up design partners. So if you're interested, come work with us. Once we have those use cases figured out end to end with the design partner, that's the time we want to scale out and offer devices, software, services, and use cases at scale as products.
Thank you, Vijoy. And the final question for you is that what is the relevance of this announcement with the previous milestone announced by Cisco?
Sorry, the previous milestone.
The hardware, I believe. The question is not clear, but I believe that means hardware. Yes.
So let me just show this stack again. And what we announced back in May was what you see at the bottom left corner of this picture, which is the photon entanglement source chip. It is a hardware silicon device that generates more than 200 million entangled pairs a second, of entangled photon pairs a second at room temperature over existing fiber. And that was the first foray of Cisco into quantum networking. And this is a hardware proof point. Today, we are announcing the quantum compiler, which you see on the top left. And it's based on this common protocol stack. It's based on a device layer, API layer that actually abstract abstracts both real hardware as well as emulated and simulated hardware. So we are building out the stack, and what we are announcing today is the software stack that you see. So we're announcing the compiler, the set of common protocols that the compiler runs upon, and the abstraction layer for real hardware as well as emulated and simulated hardware, so that we are building this holistic stack to enable distributed quantum computing.
Thank you, Vijay. With that, we are perfectly on time, and we move on to our next keynote speaker. So our next keynote speaker is Daniel Leider. Daniel doesn't need an introduction. He is very well known to everybody in quantum community. But nevertheless, I make a brief introduction. Daniel is a Viterbi Professor of Engineering at USC. He is the director of the USC Center for Quantum Information Science and Technology, director of USC IBM Quantum Innovation Center, and co-director of the USC Center for Quantum Computing. His research specializes in quantum information processing, and the key focus area for him is quantum error correction, quantum control, adiabatic quantum computing. He's recognized leader in quantum computing community with many honors and prizes and fellowship, including Fellow of IEEE, Fellow of APS, Fellow of AAAS, as well as the recipient of the Guggenheim Fellowship. With that introduction, Daniel, please, floor is yours.
Thank you, Reza. Can you hear me well?
Yes, perfect.
Okay, well, good morning, everyone. It's a pleasure to be here virtually at Cisco's Quantum Summit. Since Reza kindly invited me to give the first talk, I thought I'd present a bit of an overview. Use some of the major developments in the field, and I'll emphasize some of the work my own group has done in this area. I also apologize in advance for leaving out many equally or more deserving results by others. So I titled my talk, The State and Impact of Quantum Computing. Let me start with the impact. One undeniable impact is the unifying effect of quantum computing. It's one of the few remaining bipartisan topics. And indeed, in 2018, then Senator Kamala Harris introduced the Quantum Computing Research Act. What ended up actually passing was the National Quantum Initiative Act, which was introduced by Lamar Smith, a Republican House member. And the NQI provided an initial $1.3 billion in funding for basic research. And since then, funding for quantum computing has held steady, and currently Congress is pursuing reauthorization of about $2 billion. But let's rewind to the beginning. It's well known that Feynman is credited with the scientific origin of quantum computing. So what motivated him more than 40 years ago? Well, in his own words, the problem is, how can we simulate the quantum mechanics? We can say, let the computer itself be built of quantum mechanical elements which obey quantum mechanical laws. In other words, Feynman was interested in what we nowadays call quantum simulation. That is, when quantum computers simulate other quantum systems. The world didn't pay much attention for the next decade until famously Short announced his factoring algorithm, and suddenly interest exploded. Lucky for me, this was also right around the time when I first heard about quantum computing, and like many, I've never looked back. So what is the current status of factoring using Shor's algorithm? The state of the art is actually from 4 years ago, and it is factoring 21 with 70% success probability. And to factor a practically irrelevant number, such as a 2048-bit RSA integer, will, according to the best available current estimates, require about 1 million physical qubits. This is all still very far off. So to discuss the current state of quantum computing, let me focus on more attainable near-term goals. Now let's return to quantum simulation. The goal, as Feynman originally envisioned it, is to demonstrate that a quantum computer performs a useful simulation task of another quantum system with a quantum speedup. And this certainly remains the most natural problem for quantum computers. It allows testing of interesting physical models, it presents lots of potential applications. So to start off, let me describe a quantum simulation result I was involved in a few years ago. And this was a collaboration led by the D-Wave team. It used a 2000 qubit superconducting quantum annealer. And the goal was to test the predictions of the theory of the Kibble-Zurich mechanism. This is a theory that describes the formation of what we call defects due to diabatic excitations, non-adiabatic phenomena. We considered a 1D ferromagnetic or anti-ferromagnetic chain of L spins. Now, please focus on the top right panel. As the transverse field schedule lambda of S is decreased, and the Ising-Hamiltonian schedule J of S is increased, they cross. The crossing marks the critical point where phase transition happens between the paramagnetic, that is disordered, and the ferromagnetic, ordered phases. And when this transition is crossed fast, meaning non-adiabatically or diabatically, that's when defects form. These defects are kinks, where the spins aren't aligned properly in the ordered phase, as you can see in the middle panel on the right there. The kink density depends on the annealing speed. And the bottom panel shows two examples. These are experimental results. On the left of a fast 4.8 nanosecond anneal with lots of kinks. And on the right of a relatively slow 49 nanosecond anneal with fewer kinks. These are experimental results for a 2000 qubit chain. Now, without going into detail, let me say that the remarkable finding of this work was a truly outstanding level of agreement with the predictions of closed systems. That the kink density scales as 1 over the square root of the annealing time. This is the prediction that corresponds to the quantum annealing, the quantum annealer evolving perfectly unitarily, i.e. coherently, without any noise or decoherence. And this may sound very counterintuitive, but the explanation is that we operate at the D-Wave QPU on the nanosecond timescale, far outside the standard adiabatic regime where thermal effects and decoherence play a significant role. So this experiment proved that we already have systems with thousands of qubits that can serve as coherent simulators of closed system dynamics. Now, building on this result, the D-Wave team recently published a very interesting example of a quantum advantage in quantum simulation. I was not involved in this work. And here the task was to sample from bit string distributions generated, again, by rapid, non-adiabatic, coherent quantum annealing of the transverse field Ising model, this time for Ising spin glasses on various graphs. They compared the QPU results to state-of-the-art tensor network methods, such as MPS and PEPS. And the result they found is that their QPU can accurately sample non-equilibrium quantum dynamics well beyond the reach of these state-of-the-art tensor network methods. For example, for the bi-clique graph case, that's shown in, what is it, pink or purple there. If you look to the right, you'll see that a 7 nanosecond run on a 100 qubit system yielded samples that would take 1 million years on Frontier, which is today's most powerful classical supercomputer. This type of result is an example of the major impact that quantum computing has already started to make. That is, quantum advantage via quantum simulation has arrived. Many other quantum simulation examples exist. I've cherry-picked one or two that I'm very familiar with. And as predicted in this review paper by Daly et al. From a few years ago, we are rapidly approaching the era of practical quantum advantage in quantum simulation. Now, let's switch gears to quantum supremacy. The quantum advantage in quantum simulation result that I just told you about is actually closely related to Google's well-known quantum supremacy result from 2019 on random circuit sampling. And there too, the task is to generate bit string samples using a quantum computer. The main difference is that in Google's case, the circuit was a random one, as opposed to a circuit corresponding to the Hamiltonian of a physical system, which is what the D-wave experiment was about. Now, Google famously used their 53-qubit Sycamore chip to generate such samples. Can you hear me?
We can hear you, Daniel.
Yes? Okay, because I was getting error messages that my microphone
The
was disconnected.
microphone got disconnected middle of this slide. Correct.
So you've been hearing me the whole time? Everything?
No, I mean for the last few seconds of your talk, we couldn't hear, was disconnected. Now we can hear you.
Okay. In that case, let me return to where I was. And can you hear me?
We can hear you perfectly.
Okay. So now we actually know that this task of random circuit sampling that Google did in 2019 can actually be done much faster. And today's optimized tensor network methods running on a large cluster of about 1,500 GPUs can solve this task about 7 times faster for the 20-cycle 53-qubit scale of the 2019 Sycamore RCS random circuit sampling task. But despite this, quantum supremacy is probably safe, since it's based on a problem that is conjectured to be exponentially hard classically. And indeed, in a paper from last year, Google claimed that a 67-qubit random circuit sampling task on their updated QPU would take 10 to the 13 years on Frontier. And a group based at USTC in China claimed that an 83-qubit random circuit sampling task they executed on their QPU would take 6 billion years on Frontier. These claims have not been challenged, and I think we can safely conclude that the era of quantum advantage via random circuit sampling has also arrived. Now, as impressive as these simulation and supremacy results are, it's important to point out a couple of caveats. First, these are examples of a quantum sampling advantage. The correctness is judged by a statistical metric of how close the measured distribution of bit strings is to the ideal distribution. Second, and more importantly, the quantum advantage actually isn't ironclad. All formal proofs of a speedup depend on certain unproven computational complexity conjectures of the P is not equal to NP type. Or more precisely, no classical polynomial time sampling algorithm exists unless the polynomial hierarchy collapses. And this raises the question, can we demonstrate an experimental quantum advantage, not in a sampling setting, but rather for be done in a fully conjecture-free manner?
Daniel, we get an interrupt of audio again. Your microphone again is interrupted. Yeah.
Let me try to switch to earphones. Can you hear me now?
What is it is not very good quality. Can you talk again?
Hear me?
No, it's not understandable, your audio.
Let me. Can you hear me now?
No, it's still we have problem.
Can you hear me now?
Yes, it's good.
Oh, Good. Okay, great. Okay, I think we should be safe now. All right. So, so again, these results raise the question of whether we can demonstrate an experimental quantum advantage, not in a sampling setting, but rather for function evaluation. And can this be done in a fully conjecture-free manner? Doing this is what I call an algorithmic quantum speedup. Now, while these quantum simulation and supremacy demonstrations explicitly avoid quantum error correction methods, a demonstration of a quantum function evaluation advantage does require methods to overcome noise and decoherence. The problem, however, is that quantum error correction is both complicated and costly. It requires at least 5 physical qubits to encode one logical error-corrected qubit. And to do quantum error correction fault tolerantly requires many more qubits. For example, using concatenation, the surface code, QLDPC codes, etc. And then about 99% of quantum circuit execution time must be devoted to error correction operations. A great deal of attention is being devoted to quantum error correction, but is there something lighter that can be done meanwhile? My group has done a lot of work on this problem, and we have found that yes, we can get quite far using quantum error suppression instead of error correction. The workhorse in this case is dynamical decoupling. I don't have time to explain this method in any detail, but suffice it to say that it is a quantum control technique that uses frequent pulses to average out the system-bath interaction that causes decoherence. And it can also be used very effectively to average out or suppress unwanted coherent interactions, such as qubit-qubit crosstalk. And as an illustrative example of dynamical decoupling, here is the average state fidelity of a qubit on a very early generation IBM QPU. That's the IBM QX5 from 2018. The black line is the fidelity without dynamical decoupling, which drops very rapidly. And then the red line is the fidelity when we applied dynamical decoupling. And already then we were able to slow down the fidelity decay by a factor of about 6. The current results are significantly better, as I'll show shortly. So armed with these methods of error suppression rather than correction, let's return to the problem of demonstrating quantum speedup in function evaluation. I'll briefly mention 2 examples, both of which can be considered examples of what I like to call quantum bitstring guessing games. The first is a modification of the Bernstein-Vazirani problem, which requires the player to guess a secret n-bit string by querying an oracle that returns 1 bit for each query. And the second is a modification of Simon's problem, where the player needs to guess a periodic function's secret period. This is done by repeatedly querying an oracle that returns the function's value for each query. Simon's problem was, in fact, the precursor to and the inspiration for Shor's algorithm. The main caveat is that there are no practical applications of these bitstring guessing games other than playing Jeopardy, perhaps. But the important point here is that in this case, the quantum speedup is absolute. That is, it's a provable and completely conjecture-free algorithmic quantum speedup. As you'll see, compilation of the circuits for these 2 problems, Bernstein, Vazirani, and Simons, with dynamical decoupling is the key that enables us to demonstrate quantum speedups. So first, here are the results for the Bernstein-Vazirani algorithm run on 2 previous generation 27-qubit IBM QPUs called Montreal and Cairo. The vertical axis is the time needed to guess a secret n-bit bit string on a log scale versus the number of bits n. The white background lines are the classical time, which scales as 2 to the n, and their slope is 1. The dashed lines are the time an ideal noiseless quantum computer would require. And the scaling here is order n. And the lines for Cairo and Montreal are different since we're factoring in their actual gate and measurement times. The data points, which you'll see here, are the actual experimental results.
And as you can see, the slopes asymptote to values larger than 1. This means a quantum slowdown, unfortunately, because I'm sorry, I think I'm, no, we're good, yes. Yes, so these, again, the data points are the actual experimental results. And as you can see, their slopes asymptote to values larger than 1. Right? Their values are 1.13 and 1.28. And this means a quantum slowdown, since the quantum slope is greater than the classical slope. Again, these are the results without dynamical decoupling. And here are the results with dynamical decoupling. And the Cairo slope in blue is just about 1, so it ties with the classical case. But clearly, the Montreal slope is now substantially below the classical slope. Right? That's the orange curve. And this is therefore a demonstration of an algorithmic quantum speedup. And as far as I know, it's the first example of a fully conjecture-free quantum speedup. The speedup is polynomial, since the quantum scaling is still exponential, but it has a smaller exponent of only 0.6 compared to the classical exponent of 1. Now let's consider Simon's problem. And very recently, we published our work on a modified version of Simon's problem, which we ran on 2 127 qubit IBM QPUs, Brisbane on the left and Sherbrooke on the right. And what is shown here are the results first without dynamical decoupling, using up to 58 qubits. The vertical axis is now the log of the number of queries needed to get a secret function's secret period, to guess a secret function's secret period, versus the number of bits in that period. And the dotted yellow lines are the classical scaling, which is polynomial for a modified problem, but where we fix the Hamming weight of the secret period. And the gray dashed line is the scaling of the ideal noiseless quantum algorithm, which is polylogarithmic. The blue symbols are the experimental results, which are already clearly better than the classical scaling. But now let's add DD, which is shown in red. And the result is significantly better than without DD, dynamical decoupling. In fact, we can confirm with a careful statistical analysis that the scaling is best described by a polylogarithmic fit. And since the classical scaling is polynomial, this therefore amounts to another example of an algorithmic quantum speedup. But this time, the speedup is exponential. So we can conclude that quantum advantage has also arrived in function evaluation tasks. Now let me wrap up with a quick teaser on how we incorporate dynamical decoupling into circuits, since this is the key aspect of the quantum algorithmic speedup demonstrations I just told you about. And I've actually co-founded a company called Quantum Elements that builds products based on the approach to circuit performance optimization we've developed in my group. On the left is an abstract circuit for the Bernstein-Vazirani problem. And on the right is a transpiled version of such a circuit, designed in this case for a Rigetti processor, which uses I-swaps. The key observation is that every qubit has substantial, what we call idle gaps. These are times during which the qubit is just sitting there idling. And this is due to the fact that it has to wait for I-swaps to be executed between other pairs of qubits. And these gaps, these idle gaps, are precisely where we can insert dynamical decoupling sequences. The reason that doing so is a good idea is that rather than letting the idle qubits decohere, we can protect them in this way and suppress their decoherence. And here is a schematic, what it looks like when we insert our DD sequences. As you might have noticed, all these idle gaps have now been filled with pulses. Essentially, every idle gap receives a DD sequence. What is shown here schematically is doing that in terms of the so-called XY4 sequence. The company that we started, Quantum Elements, has a proprietary code that optimizes the choice of DD pulses and their placement. And this leads to greatly improved circuit performance and to the type of speed up result I just showed you for the Bernstein-Vazirani and Simons problems. Now, please reach out to me if you'd like more information about what we do at Quantum Elements. So what is the current state of quantum advantage demonstrations? Random circuit sample has already reached the classically intractable regime. Quantum simulation has not just reached the classically intractable regime, but it seems quite possible that practical applications are on the horizon. In my assessment, this is where the killer apps of quantum computing are, or at least are going to be in the near future. For function evaluation, we now have experimental demonstrations of conjecture-free quantum speedups. And finally, I didn't have time to discuss our results in approximate optimization. And let me just mention that very recently we published a paper that demonstrates a scaling advantage against the best-in-class classical algorithms for approximate optimization. This work builds on the realization that exact optimization is most likely the wrong target for quantum computers, at least in the NISQ era. Once we relaxed the target to approximate optimization, we were able to identify a regime where quantum annealing exhibits better scaling than today's best classical optimization algorithms. Read more about it in the PRL reference listed there. To conclude, I can't overemphasize the importance of advanced compilation methods, which are some of the subject of this meeting, in achieving some of the results that I've described here, in particular the last two. Compilation methods play at least two critical roles. They minimize the circuit depth given limited qubit-qubit connectivity, such as is typical in, for example, superconducting processors. And they allow us to optimize the integration of error suppression into algorithms, without which we would not have been able to demonstrate the speedups I told you about today. I think that a major near-term challenge is to develop adaptive and highly flexible compilation strategies. This is essential given the variability of different computational paradigms, such as the circuit model versus quantum annealing, and also given different quantum error correction strategies. And I very much look forward to hearing more about what Cisco has done in this area. With that, I'd like to thank you for your attention, and I'd like to thank my extremely talented colleagues with whom I worked on the results I told you about today. And I look forward to answering any questions during the remaining time, if there is any, or the panel discussion later today.
Okay, thank you, Daniel. It was a great talk. There are a couple of questions I will ask, and we leave the rest for the panel. The question is that, is there any practical useful quantum algorithms that shows definitive quantum advantage beyond the Simons and Vaziriani's algorithm? Is there anything that you are aware of you can comment on? And the follow-up question for that is, why is so hard over the past decade to find a quantum algorithm that shows the really practical advantage?
Yeah, so as for the first question, Bernstein, Vazirani, and Simons are, like I said, not practical in the sense that we don't know of a white box version or a gray box version of these algorithms that can be used to solve problems in the real world. But remember that Simons was the inspiration for Shor's algorithm. And it's possible that we will discover some application for it. But there are other algorithms which I think are kind of low-hanging fruit. For example, perhaps the problem known as correlation, I think is a very interesting one. That is kind of in between Simons and Shor's algorithm. There are all sorts of algorithms that have to do with shallow quantum circuits that can solve algebraic problems. So there's kind of a zoo of algorithms out there that are just waiting to be tested. And the reason that we haven't seen a lot of work on them yet is, I think, precisely because what is lacking are very lean and mean type of quantum error suppression methods. And so I hope that the work that I've talked about here will inspire further inquiries along those lines. And then the second question, why is it so hard to discover algorithms? Well, I mean, first of all, we do have really a zoo of literally there is this website called the Quantum Algorithm Zoo, which lists hundreds of results. And so the common impression that there are not enough quantum algorithms out there, I think is a little bit misleading if you consult the zoo. Second, yeah, I mean, this is a very tough design problem. And we have general principles like variational quantum algorithms and various other quantum heuristics that apply in general contexts. But it's difficult to find a new quantum algorithm that hits absolutely everything you'd like, which is a very substantial speed up on a really hard problem in a way that where you can also prove that there's a speed up and so on. That's just a hard problem.
Okay. Thank you, Daniel. We leave the rest of the question for the panel. And with that, we move on to our next speaker, which is Bart van der West. He's a researcher in TU Eindhoven and QTech Research Institute, and he focuses on compilation of the quantum internet application, as well as the question of how to program quantum network application in general. With that, Bart, floor is yours. Daniel, if you can stop sharing, and Bart, can you share, please? Yeah, thank you.
Yes, thank you, Reza, for the nice introduction. And also, I'm very honored to be allowed to speak at this event. Indeed, I'm affiliated with QTech. I did my PhD there. I'm now also affiliated with Delft Networks, a recent startup here in Delft working on quantum networks. And also the work that I've been doing is part of the Quantum Internet Alliance, or QIA. I'll introduce these a bit more in a minute. And actually, I want to first talk a little bit about all the things related to quantum networks that we do here in Delft. And then I'll go into a bit more detail about QNodeOS, which is one of the things that we've been working on recently. So what we're focusing on here in Delft and at QTech and in QIA is we're working towards this goal of having a global quantum internet, which is something that would enable quantum communication applications between any 2 points on Earth. The reason why we would like this is, well, there are many different kinds of applications that are possible in the domain of security and privacy, but also in accelerating networks. You can think of some novel features like improved imaging or quantum money, and of course also scalable quantum computing by using distributed quantum computing. So a little bit about Delft. So Delft here in the Netherlands, we have quite a large quantum ecosystem. So first there is QTech, which is a research institute, part of TU Delft. There are many research groups there. So there is a group by Stephanie Wehner, by Ronald Hansson, just to name a few, but there are many other groups working on quantum networks, but also on quantum computing. There's this startup that has recently started, called Delft Networks, which is a spin-out from QTech. There are also many other spin-outs. I list a few here, but again, there are many more. Yeah, these are just a few, so you may or may not recognize these. Then there's the Quantum Internet Alliance, which I mentioned in the beginning as well. So QTech, TU Delft, is also part of this Quantum Internet Alliance. It's a European partnership consisting of many partners, both from academia and industry. And also here we're working towards this moonshot mission of having a large quantum network, a prototype network, connecting long distance quantum nodes. So just to give a bit of an overview of the kind of research that we're doing at QTech and within QIA. we have developed certain quantum network protocols. So for example, a link layer protocol, but also we've experimentally demonstrated such a link layer protocol. And we're also thinking about network scheduling protocols, so more like SDN, software-defined networking type of algorithms. And I invite everyone to look into these references listed here if you want to know more about these. We're also thinking about software stacks for nodes in a quantum network. So for example, we developed this instruction set architecture called netchasm, which is a bit similar to OpenChasm for those of you that know that. It's an instruction set architecture specifically for quantum network applications. We also have worked on node scheduling algorithms and frameworks for such scheduling algorithms. So Koala is an example of such a framework. And then we're also doing research on compiling quantum network applications. And again, I invite you to follow these references if you're more interested and want to know more. And then recently we've also published this framework, or an operating system rather, called QNodeOS. And this is actually what I will talk a bit more about in detail in the later part of this presentation. So this is just another picture to give a bit of an overview of the things that we are working on. And this is also specifically what we work on, among other things, within Delft Networks. And again, please follow the references if you want to know more. So we don't just think about protocols or theory just like in our heads. We actually also experimentally verify our ideas. So also recently we've had this major milestone of showing heralded entanglement generation between two cities here in the Netherlands, separated by 10 kilometers. And again, we recently published this first operating system for quantum network nodes. And again, I'll talk a bit more about that in a minute. Just to mention that we are also doing even more here in Delft at QTech and within Kia. We have this Quantum Network Explorer, which is kind of like a low-level introduction into quantum networks. And you can explore some applications there with some nice animations as well. And there are other software platforms like Quantum Inspire for quantum computing. And also we have various software packages for simulation, also of quantum networks. So for the quantum internet, there are many different applications that you could think of. You can divide them actually into various stages. So at the bottom of the right image, there are the more simple applications only needing entanglement generation. But if you go up this figure, you can think also about applications that need quantum memory within the quantum nodes. And also one thing I want to highlight is that in this idea of a quantum internet, there's a difference between this quantum internet and also between that and distributed quantum computing. So one difference is that we treat these nodes as independent actors. So this is different from distributed quantum computing, where typically you might have an overview and control of all the nodes involved in your distributed computation. Another thing is also that we typically expect long distances between nodes in the quantum network, which, for example, has also an effect on the communication latency, even just the classical latency between the nodes. And again, for these more complicated applications using also quantum memory, you typically have this interactive classical quantum hybrid type of logic. So there's really this mix of both classical and quantum operations. A bit about where do we run such applications. So the model that we use is we say we have these so-called end nodes, and on those end nodes, that is where the applications run. The end nodes can be quite simple devices, for example, photonic devices, which can just prepare and measure entangled states, but they can also be more complicated processing nodes, which can do arbitrary quantum computations, store memory, do logic gates on it as well. And then those end nodes are connected to each other by the network, the quantum network, which has as a service the delivery of entangled pairs. So on each node, you could make a division within the physical part, which does the actual entanglement generation. So those blue boxes at the bottom. On top of that, there is a network stack in orange. And then on top of that, there's a software stack in purple, which uses the network stack to deliver entangled pairs to the user applications. And QNodeOS, which is what I will talk about in the next part, is an implementation of such a purple box. Just to show an example of this interactive execution that I mentioned before. So for example, if you have two nodes, both nodes have some classical hardware and quantum hardware. What could happen in an application is that the client node does some classical processing, then it sends an instruction to create entanglement with the other node. Then, for example, the client node might measure the qubit, but the server node might actually keep its qubit in memory, so you still see the purple dot on the right. Then the client might send the classical measurement outcome to the classical hardware, send it through a classical channel to the other node. The other node, so the server node, then gives an instruction to execute quantum gates on the quantum hardware, does a measurement, process the outcome, and then send the message back. So again, I just want to highlight really this mix of both classical and quantum operations, and also the mix of quantum, classical and quantum communication. So there's all these kinds of different types of processing that need to happen. One thing to highlight here is that in general, this means that quantum memory needs relatively long coherence. So for example, the server qubit needed to stay in memory while we were sending this classical message. And also, since nodes typically have to wait, this presents some opportunities to actually do concurrency, namely, for example, working on other applications while having to wait for a remote message. So now I want to go briefly through QNodeOS, which is an operating system for quantum network nodes. So the idea is that each node runs its own instance of QNodeOS. So the classical part, or like the part managing the classical execution of applications, we call it the CNPU, Classical Network Processing Unit, and it executes the application source code. We wrote an SDK for it in Python. Then this CNPU translates the application instructions into netcasm subroutine. So netcasm is again this instruction set that I mentioned earlier. And then there's the QNPU, the Quantum Network Processing Unit, which then executes these netcasm instructions. And one of the responsibilities is also to communicate with the QNPU of other nodes in order to synchronize and prepare for actual entanglement generation. And then the QNPU talks to what we call the Q device, which is the actual quantum hardware. And so it is the quantum device, the Q device, that does the actual entanglement generation. But again, it's all controlled by this stack above, like the CNPU and the QNPU. And also we made sure that that everything above this dotted line, so basically everything from the QNPU and the CNPU, except for the Q driver, is fully quantum hardware independent, meaning that you can actually swap out different types of Q devices. So you can use different quantum technologies for your nodes and still be compatible with our operating system. So briefly, just some design considerations and challenges that we had while creating QNodeOS. First of all, this interactive execution. So the idea here was that we have these different parts, so the CNPU and the QNPU, each with different responsibilities to handle both the classical and the quantum execution. So this hardware abstraction layer is used to be compatible with different kinds of quantum devices. Also, these three parts CNPU, QNPU, and QDevice work on different timescales. We need that because, for example, the actual physical quantum entanglement generation needs to be very precise. So there needs to be synchronization on the nanosecond scale, whereas the CNPU, which sends classical messages, like in a standard network to other nodes, might work on the millisecond scale. Since quantum memory has limited lifetime, we need to do some clever scheduling such that quantum states are in memory as short as possible. Then we also have the distinction between local operations and network operations. So we separate them in a network process and also in user processes. And also the concept of user processes allows us to actually have multiple user processes, which means that we can actually concurrently execute multiple applications at the same time by switching between the user processes, just like in a classical operating system. So here on the top right, you see an example of the interplay between a user process and a network process. So the user process might request some entanglement, and then at some point the network process is activated, which then triggers the QDevice to do the actual entanglement generation. When entanglement is ready, it will give control back to the user process, which then might, for example, measure the entangled qubit, depending on the application logic. On the bottom right, you also see some components of the QNPU. So one thing to note there is we have this concept of entanglement request sockets, ER sockets. So this is an abstraction similar to classical sockets. The idea is that applications can open an entanglement request socket with an application on another node, and then QNOD-OS handles the mapping of entangled qubits to these sockets. So we did a demonstration of QNOD-OS. So we have a 2-node quantum network here in the lab at QTech, based on NV centers. And so we successfully tested running QNOD-OS on those 2 nodes. And also we did an experiment using the quantum hardware of the Innsbruck University using trapped ions, thereby showing that indeed QNOD-OS can handle multiple different platforms. So here are the results of the experiments that we did on the NV quantum network. So we executed the circuit in the top left. So there's a server node and a client node, and they start by entangling, so creating an entangled pair. The client then measures its qubit, and at some point it sends as a classical message a particular value to the server qubit. And all that time, the server actually kept its qubit in memory. And in our case, it had to keep this qubit in memory for about 5 milliseconds. And then when it got the classical value, the server acted on it by doing certain rotations and then measuring. And so this way we showed that QNOD-OS really could successfully execute this application of dedicated computation. And if there are many more details, of course, about QNOD-OS and also the experiments. So again, I refer you to the reference, so the Nature publication, if you want to learn more about this. And I want to just briefly end with a bit of a promotion of Delft Network. So this again is like a new startup here in Delft. The idea is that we work on quantum networks. One of the things we want to do is commercialize QNOD-OS. And actually we are hiring as well. There are multiple positions open. So please reach out to us if you're interested. And with that, I want to thank you for your attention.
Thank you, Bart. A great talk. There is a couple of questions. I asked the first one, maybe then we leave the others on the panel. So, what is the real is there any real scenario or use case for interactive classical quantum execution in such a way that QNode OS is doing? Do you have any application, practical one?
Yeah, so I have to say the experiment that we did was quite small scale. So of course it was on a 2-node network, and actually both nodes just had a single qubit. But this was just a limitation of the physical setup. So in principle, QNode OS works with larger networks and also with nodes that have more qubits. And then one application that you could think of is, for example, something called blind quantum computing. With blind quantum computing, the idea is that a client is interested in performing a certain quantum computation, but it actually delegates this computation to another node because maybe the client doesn't have a large enough quantum computer. So there's this server which has a large quantum computer and can execute the quantum computation on behalf of the client. However, with this blind quantum computing protocol, the client can actually make the server do the computation without the server knowing which computation it does. And so, the intuition there is that because the client and the server communicate using entangled pairs, the server doesn't fully know the state that it's operating on. And therefore, the server does certain operations, but it doesn't know what it means. But the client does. And so, therefore, the client can basically securely do remote computation. So that could be an interesting example, which also QNode OS enables.
Okay. Thank you, Art. That was a great talk, and we will follow up with the rest of questions in the panel. So we are moving on to next talk. Next talk is from Cisco, which I am very proud to announce that the team here is a 3-person team is going to present the Cisco's compiler. We start with Enid Kaur, which is the technical lead in Artorian algorithms. She's gonna do a deep dive in the compiler functionality and features, and then we follow with our engineering technical leads, Sam Olds and Adam Lawrence, which are gonna do a live demonstration of how compiler works and how you can use it. So with that introduction, Enid, the floor is yours.
Thank you, Reza. Okay, hi, I'm Enid Kaur and I'm a quantum researcher at Cisco. And today I will be talking about the network-aware quantum compiler that we are developing here at Cisco Research. Okay, so as we move towards fault-tolerant quantum computing, we are going to need millions of physical qubits. And that's not going to come from a monolithic device. It will come from scaling out with multiple QPUs connected through a quantum network. At Cisco, we are working towards achieving this quantum network. The quantum network that we envisage, it's high fidelity and hardware agnostic. This means that we aim to talk to superconducting qubits, charged atoms, and neutral atoms, among various quantum technologies. The compiler that we have for distributed quantum computing, it handles non-local gates, entanglement scheduling, and resource contention across QPUs. This compiler, it can also handle multiple quantum circuits in a quantum data center type setting. Okay, so when it comes to the Cisco quantum network hardware, we have 3 components for now, which is the telecom source. So this is a chip scale entangled photon source developed with UCSP. We have a dual frequency source, which is developed in collaboration with QNect. It uses a rubidium-based atomic ensemble, producing 2 photons, one in near infrared and one in telecom. We're also developing a quantum switch. It's a programmable platform that routes entanglement between nodes while preserving their quantum coherence. So let's come to the quantum data center architecture. So this is like the cornerstone of the compiler that we have. It's basically a high-level blueprint for quantum data center architecture, and it's built using many of the components, hardware components that we have just discussed. So on the left, we have a clause-based topology. So each rack, it hosts multiple QPUs which are connected via near IR switches, and those racks are interconnected with telecom switches and capable of performing Bell state measurements. This setup, it supports modular scaling within and across the racks. Okay, on the right, we have a B-cube setting, which provides richer connectivity and greater path redundancy. So here the entanglement is routed through near IR switches. More importantly, what I'm showing you here, it's a generalizable blueprint. So while we are talking about clause topology or B-cube topology, the compiler that we have developed here at Cisco, you can use that for performance analysis pipeline, and you can put in your arbitrary topologies, whether it be FAT3 or Butterfly or any other network design optimized for distributed quantum computing. So the compiler that we have developed, it can help you test out how the architecture performs within our framework. Okay, so when we talk about distributed quantum computing, one of the major purpose of the network becomes entanglement distribution. So in this, we assume that each of the QPUs, so in a compiler, you'll have QPUs connected by networks. We assume that each of the QPU, it has a communication qubit to generate and store entanglement. So there are three primary entanglement generation protocols we consider in our architecture. The first one is the emitter scatterer. So here we assume that the QPU that we have, it has one communication qubit which is as an emitter, and the other QPU, the communication qubit acts as a scatterer. In the next protocol, which is the emitter-emitter, in both the communication qubit, they act as emitters, producing a photon that are routed to a central Bell state measurement module. Next, we have a scatterer, and in this case, both the communication qubit acts as a scatterer. There is an entanglement source in the middle, and the photons are sent to the BSM, which performs a swapping. Now, each protocol, it comes with a different fidelity, a different success rates, and timing constraints. And depending on the network setup, we can select the appropriate one. In our current compiler, you can choose the protocol accordingly. Okay, next going to the software stack behind our quantum data center. So at the top, we have the compiler layer itself. So this includes the circuit partitioning, qubit mapping, distributed error correction, scheduling, and multi-tenancy. And this is going to be the focus for the rest of my presentation. And this is what Sam and Adam are going to talk about later on. In the middle layer, we define a library of common quantum network protocols like entanglement distribution, swapping, teleportation, measurement modules. So these are modular and composable and form the network logic layer that the compiler talks to. At the bottom, we interact directly with the quantum network devices. So you have your sources and switches and measurements. Depending on the application we have, it can be real hardware, emulated or simulated. So right now, because we are dealing in the data center regime and distributed quantum, we are in the simulated regime. Okay, so now I'll be talking mostly about the distributed quantum computing compiler. So let's look at the software architecture. So we begin with a circuit, usually that is CASM or Qiskit format. It gets transpiled and prepared for distributed execution. At this stage, the user can select an error correction scheme. So right now we support surface code and bivariate, though you can select your own error correction code. Okay, so you can construct your own error corrected circuits and codes. And once we have encoded the logical circuit, we incorporate the network characteristics and the topology. So this includes architecture layout, entanglement generation protocol, coherence times, and available bandwidths. Okay, so after you specify the circuit, it's transpiled, you specify the network characteristics, we move on to the partitioning module. So here, the circuit is broken across QPUs. We then go to the QPU, the qubit mapper, and that's followed by our scheduling simulator, which basically estimates the latency and its impact on decoherence. Now, this is crucial for figuring out where the performance bottlenecks come from. And finally, after all these components are connected, we go to our performance analyzer or performance analysis module. So this lets us evaluate different configurations and different heuristics. And a key point here is that this whole flow in our compiler, it's designed to be modular. So you can plug in your own partitioning strategies or you can write in your own scheduling rules. It's built to be flexible. Okay, so now I will focus on various components in the compiler itself. So we assume that the user has specified the circuit under consideration as well as the network topologies and the characteristics. So let's go to the first module, which is the circuit partitioning. Okay, so the goal of this module is to group the qubits in QPU and identify which gates are non-local and how should they be implemented. So this is our window-based circuit partitioning approach. It's designed to minimize entanglement overhead while allowing for dynamic qubit allocation. So first, let's talk about the gate partitioning. So you're given this circuit. So you have your qubits. Right now you see only 2 qubit gates, but that can be changed. So the first is the gate partitioning module. So what you do is construct a graph, and each qubit is a node in that graph. The edges correspond to the 2 qubit gates, and the weights on the edges, they correspond to the frequency of the 2 qubit gates. After you construct this graph, we pass it through a graph partitioning module. So this can be an KL algorithm or METIS or any other graph partitioning algorithm. Now, what this partitioning algorithm does is to group highly interactive qubits together, ideally on the same QPU. So now any gates across the partition. So partitions basically is qubits grouped together. Any gates between those groups of qubits, they are non-local gates and we need entanglement to implement them. Okay, so in the gate partitioning module, these qubits, they are fixed to the QPUs and they are not dynamically moved. Next, we come to the WBCP, which is the window-based circuit partitioning. So we start by slicing the circuit into temporal windows, shown here along the timeline of the circuit. And within each window, we do circuit partitioning. But here's the key part. The qubit placement that can evolve over time via teleportation. That is, qubits can move between QPUs, but we only accept the placement when it actually lowers the EPR consumption. Okay, so in addition to the WBCP, we also have 2 additional optimization passes in our compiler. So the first one is the gate packing. So this basically is like if you have a qubit which interacts with the same remote QPUs multiple number of times, you can group those gates together and use one EPR pair to implement that set of gates. This reduces the number of EPR pairs consumed and the total latency. We also have the intra-subcircuit state teleportation. So instead of allowing teleportation only between windows, we sometimes allow teleportation within the windows. So if a qubit repeatedly interacts with the same remote QPU, we can teleport the state once and then get it back to the original QPU. This is a bit more aggressive optimizations, essentially relocating the qubit temporarily, but it reduces the cost. So depending on the circuit structure, you able appropriately choose the optimization. Okay, so in the compiler, you'll see that there are 3 choices of our circuit partitioning. You'll have a base algorithm. We've talked about all of them. The there is a difference, so depending on how the dynamic allocation takes place, but the major difference also comes in timing. So this has lower complexity, and then as you go down, your complexity of the algorithm increases. Okay, so now let's talk about the qubit mapping. So specifically, where to physically place the QPUs in the data center. Um, from the circuit partitioning, we already know how many EPR pairs are needed between each QPU. And from the network, we know which links are slower and noisier. And not all links are created equal. And we use an ILP formulation to basically assign these QPUs to the data center. And it improves, basically minimizing the usage of noisier links and improving the overall fidelity. The next part that we have is a scheduler or a simulator. So once we have partitioned the circuit and mapped the qubits, we move on to this scheduling or simulator part. This deals with how resource allocation and EPR pairs are generated in the circuit. So one example we have here is the static entanglement and generation scheduler. So basically over here you see a circuit, 6 qubits and 1 qubit per QPU. It's a toy example, and each qubit is given to 1 QPU each. Okay, so what we do is we have this circuit and we have a directed acyclic graph. We basically look layer by layer. So we start with the first layer, we greedily reserve links through the network. We start with the layer, look at the disjoint paths. So over here, these are the paths that you will be taking. In the second layer, we again see, okay, there are 2 demands, but not all of them can be completed. So we generate entanglement for the first one, and then we move on to the second layer. This is a greedy scheduler reserving paths in the network, but it's extremely fast computationally. We do give 2 choices. So one is a dynamic scheduler that we have implemented and the static scheduler. The major difference in these schedulers is how they handle the probabilistic entanglement generation. The key takeaway here is that the dynamic scheduler, it adapts to circuit progress and network conditions, improving resource utilization and reducing idle time. In interest of time, I'll not be going into the details of how the dynamic scheduler is implemented. Okay, so the next part of the compiler is the multi-circuit scheduling module. This is where things get interesting. So instead of compiling a single circuit, we now handle multiple circuits submitted by different users or workloads. There are different heuristics that we have implemented for this multi-circuit scheduling as well, and Adam will go into detail on what heuristics we have. Okay, so now let's step back to the error correction. So as we move towards fault-tolerant quantum computing, the physical qubits, they are no longer our unit of computation. We work with logical qubits encoded using error correction codes like surface codes. So traditionally, these codes are implemented within a single device, but in a quantum data center setting, we have to consider how to distribute entanglement, how to distribute error correction across a network. That's where things get complex. One option is that we place one logical qubit per QPU, so self-contained, but we can also smear a logical qubit across multiple QPUs. So this depends on the resource availability and the layout. So in this figure, I show one logical qubit per QPU. And now let's say that I have to perform a logical CNOT operation. So we can perform either lattice surgery or we can do a transversal implementation. Now, in both the cases, we need network mediated entanglement and not just any entanglement. This must be high fidelity, otherwise the network itself introduces logical errors. Okay, so in our current compiler, users can start with a quantum circuit and choose the error correction module or error correction code, either surface code or bivariate bicyclic codes. We then encode the circuit using a transversal implementation of the logical gates. So there's no lattice surgery or ancilla preparation yet. These transversal logical gates, they map directly into the code blocks. So right now, we apply a syndrome measurement. So you see the QEC blocks here after every logical gate. But the structure is flexible. You can have more advanced check replacing idle time as well. Okay. Once the circuit is encoded, it flows through the rest of the compiler stack like partitioning, QPU mapping, and scheduling, exactly as I have described before. So it will seamlessly decide how to place your logical qubits in the network. Now we can analyze how distributed fault-tolerant workloads will perform across a quantum network. Okay, so coming to the challenges, we want to support adaptive network aware codes. We will be introducing lattice surgery, not just within QPUs, but across them. And we're also looking at cross-layer optimization. So where to place the magic state factories and how do we jointly tune parameters in the network. So right now, there isn't a compiler that handles all of this in a unified way. But that's exactly what we are building here in Cisco. To wrap it up, there are a few use cases we're already targeting with this compiler. So the first one is benchmarking quantum data centers. So, we can model different topologies like Claws, Bcube, and Dragonfly and see how they perform under various workloads. The second is distributed execution of error correction code. We want to evaluate how fault-tolerant gate implementations work in a distributed setting and how network characteristics impact the choice of error correction. Okay, so the compiler availability is given here on the screen. And now I will pass it over to Sam, and he will be walking us through Cisco's distributed quantum computing compiler. Thank you.
Thank you, Neat. Hi, my name is Sam Olds. I am a software engineer here at Cisco. So I'm flashing this up on the screen. This should be where you land if you follow that QR code that Anit shared earlier, but we can also share this link, I'm sure. But this is the compiler code is available. I've been working closely with the team to operationalize all of the research that Anit has been talking about into a developer-friendly toolkit. It is a Python-based thing, taking a lot of feedback or intuition from Qiskit. Qiskit's been a great example for us. So once you get your file download, once you have downloaded it, you can pip install QNDK. And then many of these things that Anit have been talking about are available for you to play around with in your local development environment. So I'm going to start off with just kind of the basic flow, talking about the pipeline that Anit was showing, taking us through initializing a quantum circuit, setting up what your data center topology and characteristics look like, doing the partitioning and the mapping, and then running a simulation and doing an analysis on the results. So this first example, we're just going to use a Qiskit circuit, a kind of simple toy example like Anit was showing. Just a couple of CNOT gates over 8 qubits, and then we're going to define what our topology looks like in our data center. So here in this example, we're going to do the class topology, and I'll talk about this more later, but this is how you would define the hardware characteristics in the of each of the nodes in the topology. So here's what this topology looks like. These are top of rack switches. These would be the near IR switches. These ones up here would be the telecom switches. And then there's basically one QPU per server rack. And in this example, each QPU has a total of 4 qubits. So next we are going to use the window-based circuit partitioner that he was talking about, and we're going to partition up our circuit that we had defined, and we can see how it gets mapped into our data center here. It is going to span across these 2 different QPUs. But again, like Anit mentioned, we want the partitioning to be intelligent. You want to keep logical groups of qubits that have a lot of interaction with each other local. You want to maximize your local gates and minimize your non-local gates. So this partitioning algorithm will do that. And then we enter the scheduling simulator step. And here we're going to plot this. This will basically step through the circuit and analyze any sort of network operations that are required to execute that circuit distributedly. And then you can plot what the shared network resource usage is over time. So in this case, these are Bell state measurement readings that are taken over time. So in the first execution step, there's one Bell state measurement reading that was required, which indicates the number of entangled pairs that are needed to perform that non-local gate. So if we were to switch up what our topology looks like a little bit, keep that same circuit that we were using earlier, repartition, map it back onto the topology. Here, there's going to be many more non-local operations. And so we can resimulate it and see kind of how the shared network resource usage over time is impacted. So the next thing I want to dive into a little bit is taking a little bit of a deeper look at the circuit and how the circuit gets partitioned onto the network and what's happening at each of those execution steps. So we're going to reuse this same circuit here, and we're going to plot it onto this kind of topology. So here again, there's going to only be 2 QPUs, 8 qubits total. So there will be some non-local operations in this specific example. And here, this is a directed acyclic graph. This is another representation of the series of operations that happen as the circuit is executing. So each of these green nodes are a qubit. The blue ones are the gates that are happening between the qubits. And Qiskit does a good job of having a representation like this, but we have enhanced it a little bit further with the network events that are happening. So right here at this node, this must be a non-local gate, which means that there is an entangled bit that would be required, which means that at this switch, a near infrared switch, there'll need to be entanglement generation that happens before this operation can be performed. So if we were, again, just to kind of drill down onto that example a little bit, look a little closer at a different topology that has a lot more of those non-local gates, we can see there's going to be a lot more non-local gates, more EPR generation that's going to be required. So this can kind of give you an idea. If you want, you can look at this like exact execution log. I want to emphasize that we are using Qiskit in this example to define the circuit, but we also support QASM. You can use QASM instead. And then we have our own simulation engine under the hood that's what's actually stepping through these circuits and analyzing what events are happening, where in the network are they happening. So if I run this example, the interactivity on that other plot is not working right now, but we can step through. So here, this QPU has 8 qubits in this example, and there's 8 qubits here. And so there's this interactive graph that'll show you at each execution step in the circuit, which network devices are involved in that. So everything fits onto one QPU here in this example. But if we split it up so that there's only 1 qubit per QPU, now we can see all of the different nodes involved in each step of execution in the network and get a better understanding of maybe where bottlenecks would be in our network and how we might want to structure things differently. Okay, so we talked about the circuit. You also want to be able to define your network, your topology, and play around with different structures, different things. For this example, I'm just going to pull in a 8-qubit QFT. Anit had showed us the B-cube topology earlier, which you could use if you'd like. That's kind of what this B-cube topology looks like. But we are going to go back to the CLOS topology here. So you can define, the number of ports per switch, the number of QPUs per rack. Most of these toy examples have been a very small number of qubits, but of course you could push this up to 147 or whatever the kind of current state of the art number of qubits is, just to match your data center or whatever you're trying to test. But then the other important part of this is defining the hardware characteristics of each of the nodes in the topology, and this is how you would do that. So you would take your topology, whatever you have, and you would define. Right now, these are just kind of doing the default values for different characteristics of the QPUs. So a certain number of communication qubits, the bandwidth that exists in each of the links, the number of entanglement sources or Bell state measurement modules that exist in the near infrared switches or the telecom switches. And this is a little helper method to create a homogeneous network, but you can create a heterogeneous network if you want, where all the different nodes have different types of characteristics, and run it through the simulation. It will respect these shared network resources, and you can plot what those shared network resources look like over time, like I showed earlier. So here, if we want to, just another quick example, change some of these values, and just rerun it a couple of times, same circuit, same topology, but with just different amounts of communication qubits, for example, we can take a look at how that impacts these shared resources over time. Next thing I wanted to highlight, again, this is a Python SDK. So we want to provide a lot of different tools that you can pull down off the shelf and use. But if you have something better that you want to use, you have the ability to extend these different classes, these different functions, and use whatever you want to use instead of whatever we're providing. So here, I'm going to use another QFT on the class topology, but I'm going to write a custom partitioning function. So this partitioning function is kind of silly in practice because this is just doing round robin. You want to minimize your non-local operations and maximize the local operations, and this is not doing that. But it's pretty easy to extend the different modular components of this. We're trying to make sure there's a nice consistent interface between each of the modules so that you can plug things in as you want, and then you can still just run it through the remaining steps in the pipeline and run an analysis and get an idea of how well that worked. And then the last thing I want to talk about before handing it off to Adam is all of these examples so far have just been really small toy examples, just a couple of qubits, a couple of CNOT gates. But this is an example just pulling from Qiskit of a hydrogen molecule simulation. So if we run this, this is just regular Qiskit, and then this is what that circuit looks like. It's quite involved, quite a bit to it, but it doesn't change anything in the rest of our pipeline with QNDK. You can still just define your topology, your partitioning algorithm, all the different things that we've been talking about so far, and see how it gets mapped onto your network and run an analysis of how what the network latency might look like. So in this case, we had showed the Bell state measurement module readings over time. That was just kind of at an arbitrary time unit execution step. But here we have another way you can define the different constant kind of values in your network, the generation, the near infrared entanglement generation probability, switching delay, qubit reset, things like that, and then run a network latency estimator and see how well it does. And so here's just another example of just kind of changing these values a little bit to something that matches more closely what you're working with, and you can replot it and get a better idea of what's going on. So that's about all I wanted to show. Thank you so much for the time. I'm going to hand it over to Adam now, who is going to give a bit more of a deep dive on some of the cool things that QNDK supports. Yeah, thank you.
Thanks, Sam. Let me share my screen. Perfect. Hi, I'm Adam Lawrence. I'm a data scientist here in Outshift, and I've been working alongside Sam and Anit on the compiler. So what I'll show for you today is distributed quantum error correction and QPU placement optimization methods. In this tutorial, I'll show 3 different scenarios. The first scenario, very similar to what Sam just showed, is creating a base circuit, taking a look at its properties, running it through the pipeline, and seeing the output results, such as latency. Then using that same circuit, I'm going to apply quantum error correction to it. We'll see how the circuit has changed. We'll run it through the pipeline and then take a look at the network latency at the end. Then the third scenario is after partitioning the QEC circuit, we'll see if we can apply some QPU placement optimization to get the best QPU placement and take a look at how the latency changes afterwards. So let's begin. Down here, I create a base circuit, pretty small, QFT, size 12 qubits, and I'll apply QEC to it. You can see that the QEC circuit has now grown to 216 qubits. Let's take a look at the reason why that is. In this example, I'm running surface code. So for each of the qubits in that base circuit, you're going to get a similar looking lattice to what is shown here. Now, what's included in this? Well, for one, you now have 9 data qubits as marked here in the circle. In addition, you have an X ancilla qubit and Z ancilla qubits as well between them. If you wanted to take a look at a specific stabilizer, let's say the Z stabilizer, you can go ahead and do that as well here. Now let's run this QEC circuit. Well, first let's run the base circuit through the pipeline and see what the results are. Here you can see those BSMs that Sam mentioned over time. And in addition, we have the network latency in milliseconds. And this is for the base circuit. It was pretty small, size 12. So this is hovering around 60 milliseconds. Now, running the QEC circuit through the same pipeline, you can see that the bell state has increased pretty significantly. And the network latency has jumped up to about 750. Now, this is expected. We went from 12 qubits to 216 qubits. One of the features the compiler offers is, as we mentioned earlier, the QPU remapping optimization. It's an ILP solution, and what it takes in is the partitioning results. So running the QEC circuit's partitioning results on this remapper, we can then take that, reshuffle, and run it through the scheduler, and we can see how our results are at the end. You can see the BSMs have gone down, but what's even more impressive is the network latency has dropped around 70%. For your convenience, here are those distributions side by side. You can see the base over here at 60 milliseconds, the large QEC circuit around 753, and then the QEC and ILP with the 70% drop. Now, I do want to highlight that this ILP doesn't need to be used on a QEC circuit. It can be used on any baseline, and this is one of the modular approaches that the compiler has to offer. So moving on, let's talk about multi-circuit. Everything we've shown previously so far has been one circuit running on one topology any given number of times. But in a quantum data center, you're not going to have that type of workload. You're going to have a multi-tenant data center, and circuits are going to be coming in from all different angles. So the pipeline for running multi-circuit or batch circuits is very similar to everything we've shown, except there's one important difference, and that is the heuristics Anit mentioned earlier. For this tutorial, I'll talk about 2 different heuristics, the first in, first out, and our hybrid sorting. Now, the first in, first out is mainly used to demonstrate our sorting algorithms, optimal speed, but it's exactly what you would think. You have a batch of circuits that come in. You have a static topology. The first circuit in the batch you place on the topology. The second one, you look to see if there's available resources. If there is, schedule it. If not, then you wait. 2 important characteristics here are the execution cost. And this is a pseudo metric we've defined as local versus non-local operations, and qubit wastage. And that's how long a qubit sits idle during the execution of the batch. Now, you want your quantum data center to execute at the most optimal level. So you want to minimize that qubit wastage. You don't want qubits sitting around when they can be running smaller jobs. So we've introduced a hybrid sorting algorithm to reduce both these metrics. Now, in the convenience of time, I already have this processed. And there's a lot going on in this notebook. It will all be online. There will be tutorials. Don't worry. But let's just get straight to the results. Here you can see the per circuit latency for first in, first out. Now, what you'll see here at the bottom is the circuits. They've executed in order from circuit 1 to circuit 50. You might not see data on this chart, and that's okay. That's because the circuit was able to execute on one QPU without doing any non-local operations. So that's fine. But let's see if you wanted to take a look at a specific circuit. Here, with a hover over, you can take a look at the specific job-related results at the global view. And if you wanted to take a look at more specific results, such as the switch events, which is the near-infrared or the telecom events, you can do that as well. But what I really want to highlight here is these two graphs. And this is the timeline and that utilization. Here for the first in, first out, you can see a fair amount of circuits were scheduled right at the beginning. And well, looking at this, you can see that most of those circuits were pretty small. So they were all able to fit on the topology at the very beginning of execution. But since there are larger circuits and smaller circuits throughout the batch, you can see that the utilization, and that is at the qubit level, isn't very well optimized. You want to be running at 100% utilization, but you can see there's a very large gap between 100% and the utilization level for first in, first out. So let's take a look at our hybrid sorting approach. Now, before I get there, what is the hybrid sorting? Well, essentially you have your batch and you analyze it before. It's like playing Tetris optimized. You get to look at all the pieces in the order they come, and instead of doing one at a time, you just shuffle it in a way so that the game's over as quick as possible. So for that hybrid approach, you can see here that now the circuits aren't executed in the order that they were brought in. They were shuffled in the most optimized method. And these results are similar to what we had before, but let's look at that timeline and utilization level. Here you can see the schedule in which they were, the order in which they were scheduled. But down here, what I want to highlight is that utilization level. We're hitting around 100% on the qubits during the majority of the time. And there's a pretty quick taper off, meaning that only a few of those large jobs were remaining at the end until they finished. And so that execution overall time is now shorter, and the qubit wastage is now minimized, which is marked by this graph. In addition, we also have, as I mentioned earlier, for the outputs, job level metrics. So you can take a look not at this global view, but if you wanted to see specific circuit level results, you can take a look down there. Well, let's take one more step back. Everything Sam and I have talked about has been from the viewpoint of a researcher, a programmer, someone using this code on their laptop, running Python, and that's great. But what if you're a network engineer running a quantum data center and you don't really want to get into the nitty-gritty of the code? Well, we've provided an API suite that has all the same functionality that we talked about just now in the API version. What you can do here is initialize your topology, create your network, create your circuits, and execute your simulations. Here you can see I already have a class topology initialized. What you see at the bottom, those are the qubits. Here are the QPUs and the different devices. Now I'm going to run this execution. I already have pre-populated, so let me execute. We have our 200. The jobs are being created and they're being sent to the topology. And pretty soon you'll see jobs are being scheduled and they're color coded. And you can see them executing on the topology. And then when they're done, the resources are deallocated and new jobs are scheduled in, new circuits are scheduled in. Now, there's some pretty good cool color coding here. It's not just some groovy tie-dye we put together. And what that is you're seeing multiple circuits running through multiple devices. That's about it. I will hand it off to Reza, and thank you very much for listening to the compiler.
Thank you again, Anit, Adam, and Sam. That was a great presentation. Unfortunately, we ran over the time, although I have to admit we practice it while we ran over the time. But the questions are being answered on the Slido, and we leave the question on the panel. We need to move on to our next speaker. Our next speaker is Dr. Yehuda Nawa. He is the co-founder and CTO of the Classic. He has more than 20 years of experience in quantum computing. He founded the quantum research in IBM Haifa research lab. And now, obviously, he's a technical lead in the Classic startup company. So with that introduction, I hand it over to you, Yehuda. The floor is yours.
Thank you very much, Reza, and thank you all for being here. I would like to discuss with you the way that we view how to do modern quantum software. And in effect, it is a technology thing. As we understand, the software model for quantum is a gate-level model. This is the most robust model we understand for quantum, and it should be dealt in this way, which is gate level on qubits, meaning very close connection to EDA technology, and this is what I'm going to present right now. I'll mention the principles guiding us in terms of functional modeling and program synthesis. The two pillars. One is the model.
Yehuda, you are not sharing your screen. You need to share your screen, please. So people from Cisco TV.
Okay, thanks, Reza, for that. Once again, I'll go through the agenda. I will mention the principles of functional modeling compared to gate-level modeling, say, and program synthesis from the functional intent of the model into the machine code, the gate-level code. The two pillars are modeling constructs and then the technology, the synthesis technology. I will go over those as parts of examples. I will show you the very robust results of this technology, meaning orders of magnitudes different in all aspects, both quality of the circuit and compilation time, with regards to the common transpilation technology, which is common in the industry. The results are robust and clearly understood, so there is no argument about it. It's across the board. And then I will leave some time to show the highlights of my company Classic, and in particular our vision, and summarize this talk. So the thing that we need to solve here, once we have a functional model, the functional intent from the user, is to understand the block level decisions of how to implement each and every function, how many auxiliary qubits to use, what would be the positioning, the placement of the different blocks on the circuit. Also, accuracy is very important, both for NISQ and for fault tolerance, the distribution of accuracy, in a sense, the distribution of all the computer resources between the different parts of the program. And this in view of the system-wide resources, the number of qubits we have, the the runtime that we allow for the circuit, the overall accuracy, and so on and so forth. So this is essentially what we do. And in order to contrast it with the state-of-the-art common methods today, which are transpilation methods, let us look at the implementation space. So suppose we have any particular function, and here I draw the implementation space. Typical, a transpiler must mathematically, by definition, be correct at the gate level, meaning that if it sees two Hadamard gates, one near each other, it can eliminate both, because two Hadamard gates equals identity, but it does not have the context of whether the Hadamard gates or a more complex structure are an adder or subtractor or multiplier or multi-controlled NOT or any other function. In contrast, a true compilation or a true synthesizer will understand the functional intent of the user, and then it may choose between very different implementations, some requiring more of the qubit resources, some requiring more depth resources, more accuracy, less accuracy, keeping only the functional intent given as input and not the gate level intent, which is the input to a typical transpiler. So quite easy principles, of course, very difficult to implement. And the implementation goes through a common, robust EDA technology knowledge that was developed for 5 decades and more now for similar problems in classical hardware. And the two pillars of EDA technology, and in the sense of our technology and of quantum technology, should be the modeling constructs, understanding, this is the domain knowledge, understanding what is a quantum algorithm and what are the typical constructs that need to be viewed, need to be actually understood by the compiler. And then the synthesis technology, which takes out of, in the previous slide, it was some caricature of 3 possible implementation in implementation space. Of course, this is a continuous choice between an infinite set of implementations. So this is the well-known synthesis problem, going from an abstract, high-level functional intent into a very concrete, low-level machine code that the computer can understand. So looking first at the first pillar of modeling constructs of the language. So over here you see the most well-known picture in quantum computing, I would say. This is the Shor's algorithm, a very simple algorithm in terms of the high-level definition, some Hadamard transform, at the end, inverse Fourier transform and a measurement, and in the middle, controlled modular exponentiation. Of course, a very innovative algorithm, but the math is simple. On the right-hand side, you see an implementation of the Shor's algorithm, which can be tens and hundreds of thousands on gates, on hundreds of qubits, very, very complicated implementation, and more than that, a very flexible implementation, which depends on the computer resources. So there is a multitude ways of implementing this conceptually simple algorithm, and this is the task of the synthesizer. So in order to do that, we really should understand what are the idioms of quantum computing in terms of the modeling constructs. So it's multiple controlled gates and multiple controlled functional units such as adders, and modularity is a very strong concept in quantum computers. So it's a multiply controlled modular arithmetic, and here a multiplier, and so on and so forth, and model all those constructs telescopically up to the gate level, each time leaving a lot of flexibility in how to implement each of the high-level constructs. So once again, you can work in Fourier space in quantum computing, you can work in real space, putting an adder as a ripple carry adder in real space, or as a very simple adder in Fourier space, paying the price of a Fourier transform and Fourier transform inverse if you are working in Fourier space, and so on, so forth. Those are the modular pillars. At the end, the user writes either graphically or textually the quantum model. This is not machine code. This is the quantum model given in the language that the quantum user is accustomed to, which is writing papers. So you can see how the visual editing of the quantum model is very similar to what someone would write in LaTeX. Essentially, if I would have done a demo, you could see how the actual modeling, how intuitive it is, and then you can even produce the LaTeX picture for your circuit in any telescopic level of this model. So this is the high level model, and then it is up to the technology, up to the transpiler to come up to the compiler, the synthesis engine, to come up with the best or the most best gate level machine code. It could arrive at some runtime because, of course, the problem itself is NP hard. So we are working on an anytime solution for a given time, provide us the best solution. And here I go back to the second pillar of the technology, looking at the actual synthesis technology. Once again, for examples. So let us look at the workhorse of quantum computation, multi-controlled unitaries, or in this case, multi-controlled X-gate. This is how it would be represented in a high-level model, a very simple and intuitive way. This is one implementation, which takes 8 qubits. This is the least amount of qubits you need in order to implement an 8-qubit multi-controlled X, 7 controlled and 1 target. This is the functional intent. And then you can implement the same functionality with 9 qubits. You can also implement it with 11 qubits or 10 qubits, and this is the full lookup table. This is the input for the compiler. And if we look at larger multi-control X's, for example, for 42 qubit or for 60 qubits, you get a huge space of trade-off implementations governing both the width, the number of auxiliary qubits, the depths, the number of the circuit depths, and the number of noisy 2-qubit gates. And it is up to the synthesizer, the compiler, to look for each and any building block, for each and any functional block locally, and decide what eventually would be its implementation and come up with the best circuit. Another example, a quantum adder. So as I mentioned, you can implement it in Fourier space, you can implement it in real space. This is a real space implementation, but the result may be in place. If you do not need the inputs anymore, if the inputs are not necessary downstream the computation, you can implement the result in place. You can implement it out of place, keeping the inputs, and then you play with more qubits, but with more functionality. You keep the inputs. Also, if you put it in place, you need to first clean the dirty qubits from the inputs, which means a cost in the depths, in the number of, say, gates. We could also use a quantum Fourier transform adder, paying with a quantum Fourier transform, putting a much simpler calculation in Fourier space, and paying again in an inverse Fourier transform. Those are the considerations. Also considerations of uncomputation, auxiliary measurement, to what extent we are going to uncompute and free qubits for downstream computation. Here you would see different Grover oracles with the same functionality, with 25 qubits and deeper oracle, or 36 qubits and much shallower oracle. Then, as I mentioned, there are approximation management, whether you want a particular block in order for your entire algorithm to have 66% accuracy. How would this accuracy be distributed between the different functional blocks? So this is what we do. The results, you can see them in the paper. 0.7372, orders of magnitude results compared to all known compilation methods, whether it is Qiskit, Penny-Lane, Ticket, and others, orders of magnitudes which are very well understood across the board in all possible functionalities. So this would be quantum walk, very generic functionalities. This would be QSVT, reach much lower energies in QAWA for max click, quantum phase estimations, orders of magnitude difference, because the compilation is by technology going from high level to low level at each point, choosing the optimal path, and not a transpilation from low level to low level. Once again, VQE, you could see all those results. SAT solver, everything goes to, in terms of runtime, to exponentially larger number of qubits in the same runtime. Once again, it's written in the papers. Let me tell you a few words about our company, a team of 85 really tremendous people. We are privileged, I think, in the whole industry, but certainly in our company, to get the best talent. People love to enter this field. So 85, a company of 85 people of very distinguished individuals, currently 180 million in funding, in addition, of course, to revenues, global presence, fully patented. This is a showdown of the company. Our business model is through all those are customers, some of the other customers at this stage asked not to be named. These are part of our customers, global customers, recognized customers. They are using this technology in order to prepare their algorithms to the era of quantum computer. They need to prepare the algorithms, they need to prepare their IT infrastructures, they need to prepare the workforce, the talents. This is what they do. All those very, I would say, prestigious customers, very strong partnerships with all leaders in the company. And here I will stop by sharing our vision. I think that looking for a killer application at this stage is premature, is in a sense arrogant to some extent to think what would quantum computers doing, in the same way that when Bardeen implemented this first transistor, I don't think he could have in mind, or anyone else could have in mind, this 10 billion chip, which is doing everything for us today, from word processing and anything else. And this Sputnik, when first sent to space out of curiosity, no one could imagine it will pinpoint where to deliver our pizza for an evening snack. And this is our vision. We need to focus as a team, as an entire team, worldwide community. We need to focus on the technology, do our best to bring up the best technology fastest, and no one can envision what will be when we will be there. And I will stop here for questions. You can read my summary on screen. Thank you very much for your attention.
Thank you, Yehuda. Great presentation. As like the other speakers, I asked one question that is there, and then we leave the rest for the panel. So, in your platform, how portable is in terms of the hardware? Means that if you develop the question is if you develop application for certain company platform in your software, can you easily port it? Can you use your platform to compare performance in different hardware platform or technologies?
This is a very common use case. If you open up our platform, we are connected to all major and non-major hardware platforms. The compilation from high level to low level is entirely hardware agnostic. When we have the knowledge of which hardware we are working on, it is being taken into account as part of the compilation, but to some extent this would be a last mile compilation. This is not where the orders of magnitude advantage will come from, and the use case of benchmarking different modalities and different hardware for the same high-level function is a common use case. It is very simple to do with the platform.
Thank you very much, Yehuda. Thanks again for your time and presentation. We will follow up with the question in the panel. And now we are moving on to our next speaker. Next speaker is from IBM, Iskandar Siddiqov. He's lead architect in IBM, lead software architect in IBM Quantum. And he's responsible for open source software ecosystem for large scale quantum classical system. And his background is on distributed quantum computing, machine learning, and he also holds a degree in mathematics and computer science. Iskandar, floor is yours.
Thank you so much. Hi, everyone. My name is Iskandar, and today I'm going to be talking to you for the next 15 to 20 minutes about open source software ecosystem for large-scale quantum classical environments, which we call Qiskit. The content of this presentation is separated in two parts. First is the decade of open source software development, and second one is software for large-scale quantum classical environments. This presentation is aimed for like way larger time, so I'm going to be speaking pretty quick. So kudos to the video team who gonna keep up with me switching slides. Okay, we're gonna start with the decade of open source software development for quantum. Why is this decade with asterisk? Why is this with asterisk? Because it's almost a decade. It's actually 9 years, 8 months right now, but decade sounds cooler, so that's why I put a decade. So in this section, what I'm going to do, I'm going to talk to you about past 9.5 years, what we've done at IBM Quantum in terms of software and our products. I will start with 2016 when we first released what's so-called IBM Quantum Experience, which was the first platform that put quantum computers online. Back then, you were able to use what's so-called Composer, which you see on the right side of your screen, to construct quantum circuit and send them to execution in our hardware, which were located at IBM data centers. 2017, we released, this was the official first release of Qiskit in March of 2017. We took our internal project and we released it open source. We call it Qiskit for Quantum Information Science Kit. And as you can see, first commit was done by Jay Gambetta, who is the vice president of Quantum right now. Also this year, we introduced OpenQASM, which is the programming language for quantum computers. 2018, we introduced Transpilo, which we're going to be talking about a little bit later. We also introduced Qiskit elements. For those who remember, Qiskit was structured in 4 different elements. We still have AIR on a long-term support. 2019, we introduced Provider, which is the abstraction that allow you to execute Qiskit programs on any hardware. So you kind of write your quantum program once, and you can execute it on any hardware. So, and the Provider which gives you ability to connect to different platform and hardware vendors. 2020, updates of OpenQASM. 2021 was the runtime service. 2022 was dynamic circuits introduction, which is the quantum circuit with classical control flow. We also introduced Qiskit primitives, which are the most popular execution abstractions, which is sampling, quantum state, and estimation of expectation values. We introduced Qiskit ecosystem to highlight projects in community. 2023, we introduced serverless and we released Qiskit functions platform, functions as a service platform for quantum classical computation. 2024 was important year for us. This year was about performance and stability. So for the first time, we actually released stable release of Qiskit, which was 1.0. After almost 8 years of development, we finally made it stable. Also, what was in this release, as I said, focus for this release was performance. We're trying to make sure the Qiskit is most performant SDK for quantum computation. How we achieved that? We rewrite core internal structure and abstractions from Python to Rust. We did some memory optimization and we completely rewrote algorithms for compilation and circuit construction. So it was like huge rework of Qiskit. So from the outside, you still have this Pythonic wrapper and you have the familiar user experience of using Qiskit, but internally we kind of rewrote a bunch of internals. So that's how it looks on a retrospect, almost 10 years, which brings us to this year, right, 2025. A few more words about Qiskit. Qiskit is pretty popular. There is an organization called Unitary Foundation. Each year, Unitary Foundation conducts a survey among quantum developers to figure out what is the common trends, right? What is technology use, and etc. So last year on a foundation survey, 74% of participants picked Qiskit as their platform SDK, as their favorite SDK. Qiskit enables large ecosystem for more than 5,000 dependence projects right now. And the number that I personally like is this: 3/4 of the contributors to Qiskit are external to IBM. I can stand by this number because I was the contributor to Qiskit before I joined IBM. So yeah, I joined and this number get worse. What we also do from time to time, we're going through the popular scientific portals where gathering analytics from those platforms. And so far, IBM and Qiskit was a huge enabler for quantum computing research in general. Now we're gonna jump on the second part of our presentation. Before it was retrospect, so now let's talk about software for large-scale quantum classical environments. But before I do that, I have to mention the quantum-centric supercomputing, which is the IBM quantum vision of large-scale computational environments where quantum and classical resources work together, right, and provides you single user experience of operating on them. I'm not going to stop on the software stack. What I'm going to talk to you about is, in order to make any quantum computing software product successful, right, and being able to scale up to the future, right, to large-scale quantum classical environment, you have to be able to scale up core abstractions of any software, any quantum software, right? And we'll go through those abstractions. And first one is obviously quantum circuit, right? On the top of the screen, you can see the regular quantum circuit that you see on the textbooks and books and examples and etc. But on the bottom, you can see actual quantum circuits which are executed on hardware, on our hardware. This is, I think, 88 qubits and like close to 7,000 gates, 2-qubit gates circuit, which is, as you can see, they're growing quite a large. And that was one of the reasons why we started to do memory optimization, tuning our compiler stack, because at these scales and moving forward, we have to do this hyper optimization and take it really seriously. Within Qiskit, you probably know, Qiskit is Pythonic SDK. You can create quantum circuit by importing quantum circuit object and applying gates on top of it. Also, Qiskit supports, as I said, dynamic circuits, which is the circuits with classical control flow. Qiskit has rich quantum gates library, so you don't need to write the gates and custom gates from the scratch on your own. So with quantum circuit out of the way, next important abstraction is target or backend. What is this? This is the digital representation of actual physical device. In the case of IBM, we have this heavy hex lattice superconducting qubits formed in the heavy hex lattice topology. How do you create it in Qiskit? You import target object and you start appending the topology, start defining the topology and instruction properties for the qubits and for the gates, supported gates themselves. So pretty simple and straightforward. And the final abstraction that any software stack needs to be able to scale horizontally is transpiler. So what is transpiler? If you're familiar with classical compiler stack, Qiskit transpiler built with what's so-called pass manager, which encapsulates set of passes. Each of the pass gradually transform your quantum circuit from the original state that you intended to execute to the state that can be accepted by a quantum computer or platform. So it's basically changing the structure of it. You can think of it as like a huge graph optimization problem. That's how you do it in Qiskit. You can create a pass manager by calling the generate preset pass manager function. It will create your default pass manager for Qiskit, but This is good enough. You can set optimization levels as you want, but probably you want to have more control over passes that are applied to your quantum circuit or to quantum program. And that's how you can do that. You can import custom passes, or you can create your own passes. For example, this is poly twirling. So basically applies poly twirling on as a compiler pass. All you need to do is implement this run method, which accepts DAG circuit, which is a graph representation of quantum circuit, and do the modification of it. And that's it. So we talked about core abstraction, circuit, target, and transpiler. Let's talk about scaling. So on the scaling part, traditionally we differentiate vertical and horizontal scaling, right? So for the vertical scaling for quantum computation, it's adding number of qubits per single chiplet, right? Improve fidelity and accept all of the other parameters of quantum system within the single chiplet or single device. And that's what we've been doing on early generation of our hardware in Falcon and Eagles processors. But holy grail of any technology is horizontal scaling, or actually diagonal scaling, right? But what does it mean to horizontally scale quantum computation and quantum hardware? So you have multiple chips and you should have quantum interconnects between them. But how now, what does it mean for software stack to support this? Actually, for Qiskit, it changed nothing, almost nothing, because at the end of the day, for Qiskit, this whole topology remains the same connected graph, right? And you can still construct your target object, which is digital representation. The only difference will be is the instruction properties, which is error rates, will be a little bit higher within this edges of this connectivity graph. So this cross-chip couplers, we called M couplers. We introduced them in cross-bill hardware architecture. And what we did later on, you need to have longer range couplers as well. And that's what we introduced within the Flamingo architecture, where we have up to meter long quantum interconnects between chips, so you can connect them within the bridge. And again, for software, it changed almost nothing except error rates. So we talked about vertical and horizontal scaling with quantum resources, but we still have to cover classical interconnect, right? So you have multiple quantum resources associated to classical resources, and they are connected with classical links. For that, we have a set of, so what does it mean? So you have a quantum circuit, and this circuit does not fit into any hardware that you have. So logically, you need to split it in some chunks, right? Do the divide and conquer. For that, we have a set of add-ons we called Qiskit add-on cutting. It gives you new instruction that you can append to your circuit called move. You append this move instruction, then you can call a method to partition problem. It automatically will cut circuit into two halves. You can execute those halves later on separate hardwares or on a single hardware in a sequential manner. And then you can reconstruct the original expectation value. Obviously, any cutting knitting techniques have exponential classical overhead, but those are also viable methods. As I said, those packages sits within the Qiskit add-ons, which is reusable packages that we often use. I'm not going to spend too much time on them here, but what I want to say, Qiskit add-ons, they're high-level packages built on top of Qiskit SDK, built on top of transpiler, circuits, and target objects to give you higher level abstractions so you can use them in research directly. That's what we've been doing with our partners. So we're basically trying to accelerate quantum computing research with this initiative. And second to final thing I wanted to talk to you about is resource management. Since we're talking about large-scale quantum classical computation, right, we have to talk about resource management, aka how the resources are handled within the computational data centers. Resource management task, you can think of it as a huge, it's like multi-dimensional game of Tetris, right? You have the job blocks that you need to fit within this cube of resource constraint that you have within your data centers. What we did last year with our partners at RPI, we demonstrated first connection of IBM Quantum System and Amos supercomputer, which sits both within the campus of RPI. They connected within the same network, and they managed by a singular resource management system called Slurm. What it gives to users have the same user experience working with HPC systems. Now, quantum resource is just another resource in their disposal, so they can use it, schedule it. And from the system administrator perspective, it also gives like a lot of freedom and flexibility to control the quantum system as this data center specifically wants. So I think it's a great effort. That's how it looks. At RPI, we have Quantum System 2 and Amos supercomputer. We also have the same setup at RIKEN in Japan. RIKEN is the host Fugaku supercomputer, which is the biggest supercomputer in Asia. I think it's like 6 or 7 right now into 500. And this year, what we decided to do, we decided to open source this effort of making quantum computers native resource-to-resource management system. So we released a Qiskit Slurm plugin. So now any quantum resources can be supported as native resources by Slurm. So, and final thing that I'm going to talk is what is happening this year and what is the aim for this year. For this year, we aim to release Qiskit 2.x releases. What is the core feature of it? With Qiskit 2.0 releases, we're creating standalone Rust crate, which builds C foreign functions interface. What does it mean? Basically, Qiskit exposes C API now. What it allows you to do, that allows you to bind Qiskit to pretty much any language: Fortran, C, Rust, Julia, Python, whatever. So now you have, I think the 2.2 is end-to-end workflow will be released in a week, I think, which will have full end-to-end capabilities. So now you have similar user experience of using Qiskit, but in any programming language. And I will stop here because I'm running out of time. Yeah, I will stop here. Thank you so much for attention.
Thank you, Iskandar. That was a great presentation. Again, we have just one question to pick up from the Slido is for remote transversal CNOTs. Do you imagine doing them in one place, or do the logical qubit needs to be moved to some communication region of the respective nodes? I mean, how do you deal with that?
That's a good question. I will probably follow up with this later on because, yeah, I will.
I mean,
if you
let us know the answer, we can put it on a Slido, or you can come back in the panel for the answer. Okay.
Yeah, awesome.
Okay. That would be great. And thank you again, everybody, for joining the first half of this summit. We have a break now. Break is exactly 32 minutes from now. So we are coming back 11:30 Pacific time, US, or in exactly 32 minutes. And we start sharp on time with the rest of the presentation and the panels. We have a lot of exciting presentation after break as well. Thank you again for being with us so far. Hello, everybody. Welcome back to the second half of our summit, first day of the summit. So we have a very good set of speakers for second half of day and the panel as well. We kick start this part of the summit by a presentation from Dar Gilboa. Dar is the research scientist in Google Quantum AI. He's mainly working on the quantum algorithm machine learning for decentralized computation. He's completed his PhD in Columbia University, and he was a Schwartz Fellow at Harvard University. With that introduction, I invite everybody to listen to Dar. Dar, floor is yours.
Thank you, Reza. Thanks for the invitation. Yeah, so I'm going to talk about some applications of distributed quantum computing that I'm particularly excited about. as well as some others on the quantum AI team. So when people think about the typical reasons for building a quantum computer, the most common ones are essentially speed ups for various problems. So you take a problem like factoring or simulating quantum chemistry, or even certain combinatorial optimization problems. And the hope is that you solve these problems exponentially faster than any classical algorithm. And the catch is that problems that have these very large speedups typically require very special structure. So there's this nice figure from a paper by Scott Aronson from a few years ago, where he describes this sort of pyramid of structure. And at the top of the pyramid, you have the types of problems where we expect to have exponential speedups. These include factoring, period finding, which is sort of at the core of factoring, or some optimization problems like OPI, which has sort of been studied recently, where we strongly believe that there's an exponential quantum speedup. And then as you sort of move down the pyramid, you have less and less structure. And then correspondingly, the type of advantage you can expect is smaller. So for example, for unstructured search, Grover's algorithm gives a quadratic speedup, but we know that we can't do better. So to get a large speedup, you basically need special structure in Fourier space. You need the problem to be sparse, but also you need concentration on high degree terms, and this makes the problem hard for classical algorithms. And so you might wonder, okay, well, how many problems are there that have this special structure? Like how general can quantum computers ever be if they require sort of this very precise structure to be useful? But I would argue that this picture can change a bit if you think about other resources that are useful for computation. And so if you think, say, classical large-scale computation, it's typically a trade-off between various resources. So you have time, which is one important resource, but you also have memory, things like privacy of user data, communication, if it's a distributed problem. And you sort of trade these resources off one against the other, and each one comes with an associated cost. And the interesting thing is that, at least for some of these resources, you can get quantum advantages, but they require sort of very different structure. So one example is communication. So communication is typically studied in this model of communication complexity, which is a little different from query or time or sample complexity, which are more common models in complexity theory. And in this setting, essentially the only thing we care about is the amount of communication that you need to solve a problem. You have multiple parties, Alice and Bob, they each get their own input, and they want to jointly compute some function of their inputs. And you don't really care about sort of the computational cost of whatever algorithm they're running. All you care about is how many messages they have to send back and forth and how big those messages have to be. And it turns out that in this setting, we actually know of exponential quantum advantages that are unconditional. They don't require any kind of hardness assumption or anything like that. And they also have very natural connections to memory requirements of algorithms, because you essentially think of these two parties as the same person at different points in time. And so there's this natural connection. And the nice thing about communication complexity is there's actually a very natural problem where you get a very large advantage. And so most of you are probably familiar with linear classification. This is sort of maybe the simplest classification problem possible. Here you basically have a bunch of data points that are sort of in one of two classes. And these classes they're indicated by different colors here, and they're separated by this linear hyperplane. Here it's just a line because we're in 2 dimensions. And if you sort of learn where this hyperplane is, you can use it to then classify a new unseen point. And this is sort of a very common kind of model for different types of data. And you can think of a slightly more complex model, or instead of a hyperplane like this, we have a paraboloid, or in 2 dimensions, it's just a parabola that separates the two classes. And this is known as a quadratic classifier. And then it turns out that quadratic classification is a problem that exhibits an exponential, unconditional quantum communication advantage. This basically means that solving this problem classically requires essentially sending a number of bits that is polynomial in the size of the input. So if you imagine that these points are high dimensional vectors, you actually know that if one person has this vector, then the other person knows what the sort of paraboloid is that defines the two classes, then there's no way to solve this classification problem without sending a very large number of bits classically, so polynomial in the dimension of the problem, which is n here. On the other hand, if the parties are able to encode their data in quantum states, they can solve the problem using only log n qubits. So this is an exponential communication advantage. This problem was first studied by Ron Raz more than 25 years ago. And this problem is arguably a lot less structured than the types of problems that I was discussing before that exhibit large speedups. And so I think this sort of suggests that quantum algorithms may be useful even more broadly if you consider these other resources. And a lot of them are specifically relevant for distributed computation. And maybe if you think about, say, machine learning these days, it typically involves solving like highly distributed problems, like large neural networks like LLMs. They're distributed across tens of thousands or now even hundreds of thousands of devices. These need to communicate during training. They have to either communicate features, which are sort of intermediate states of these neural networks, or gradients during training. And communication can become a bottleneck in training in this way. And there are examples of communication that is required across sort of scales of tens of kilometers. For example, Gemini, which is Google's latest class of LLMs, the original Gemini models were trained across multiple data centers in parallel in the same metropolitan area. And so you could think of sort of a quantum analog of this problem, which is essentially a parameterized quantum circuit distributed between two parties, and think of the tasks of running inference with this model, so just like estimating some expectation value or computing the gradients with respect to all the parameters. And we can actually show that these exponential communication advantages carry over to these tasks. And indeed, we have a paper that shows that you get exponential advantages for these problems, for basically inference and gradient estimation in these distributed circuits. And you can even design specific circuits that can be used for graph classification tasks, and show that inference with these models also exhibits this exponential communication advantage. And in addition to these communication advantages, there are completely different and novel capabilities that you get when you consider distributed computation with quantum resources. And one is unclonability, which on the one hand, you can think of it as sort of a nuisance when you're trying to say like protect quantum information. It can actually be a feature when you think about, say, guaranteeing privacy of user data. So there's this common scenario in machine learning where, say Alice here has some data, Bob has a neural network, and Alice wants to run her data through Bob's network. The problem is that if Bob sends her the network, she can make copies of the weights, and if she sends Bob her data, then Bob can make copies of the data, and she basically loses control of her data, which could be proprietary. And essentially, this means that it's hard to also get compensation. You think about, say, markets that involve data. And if you look at designs of data markets, they're typically very complicated. You need some kind of mechanism to set prices, and you can't just let sort of the market and the rules of supply and demand set prices for a commodity like data, because it can be just copied indefinitely if it's classical data. So you could ask, well, what if Alice takes her data and encodes it in quantum state? Does this picture change? And it turns out that it does. And so one simple way to study this is through this notion of what we call consumability, which is essentially, you should imagine a scenario where Alice has some data, and there are a bunch of different Bobs, and each Bob wants to compute some function of Alice's data and his data. And then you can ask, okay, well, how many bits does Alice needs to send for all the Bobs to solve their problem? So we have like m different Bobs. Each one wants to evaluate a function on his input. I think the ratio of the number of bits needed to solve all m instances divided by the number of bits needed to solve just one instance. And then you could also define the quantum analog, which is sort of the number of qubits you need in both cases.
Now, there's some problems where these two quantities behave very differently. And one of them is a simple string comparison task. So here, Alice has a string, and each Bob has a string, and each Bob wants to check if Alice's string is close to theirs. And if all the parties use classical communication, essentially this consumability factor is a constant. And this is the manifestation of this idea that Alice's message can be copied and reused, essentially. If Alice sends enough bits for one Bob to solve the problem, Bob can just send this message to every other Bob, and they can all solve their problems. But if Alice encodes her data in a quantum state, the consumability is actually linear in the number of Bobs. And this means that each Bob needs essentially a fresh copy of Alice's quantum state to solve this problem. This means that then Alice can sort of get her money's worth if she knows that her data is going to be used m different times. Another example of using unclonability is related to this notion of quantum money, which is actually one of the first ideas of sort of using quantum mechanics to some useful end. It predates quantum computation in general. There are lots of constructions for quantum money in various forms. They essentially all have this property where you generate quantum state that's equivalent to your bill, your dollar bill, and it's unforgeable just as a consequence of the no cloning theorem. And then existing constructions for quantum money, they either require long-term quantum memory, or they sort of allow the bank to track users because the bank issues unique bills. And we've done recently has shown that there's a very simple construction that actually allows you to construct anonymous quantum tokens, which are sort of one-time use quantum money. And the basic idea is the bank has some very large random string. It sort of splits it up into subsets, sends these quantum states to the user, and then the user just measures. And then they get out a classical string that encodes a subset of the original string. And the nice thing about these tokens, the construction is very simple, and we're able to show that it essentially allows the users to sort of audit the bank to make sure that the bank isn't tracking them. Because the nice thing about these states is that they're all identical. Each user gets an identical state, but after measurement, you get a unique string back. And then essentially this unique string can be sent back. It can be stored in classical memory, and then it can be sent back to the bank for verification. The bank can check that this really came from a valid quantum token state. And then we also discussed some potential applications of this, essentially because after measurement, the user gets a unique string. It can be used to encode a message, and then this is useful for things like anonymous messaging, voting, and possibly other applications. And just to kind of wrap up, I give a few examples here of sort of expanding the typical design space beyond just speed ups to look at sort of other resources you might care about in large scale computation and in distributed computation. And I think this opens the door to a lot of novel types of quantum advantages that could be relevant. And there are, I think, lots of other interesting directions here that I kind of haven't had the time to really explore, but there's this vast literature on what are known as non-local games. So these are scenarios where you're in a setting where you can't signal classically, but you can pre-share entanglement, and it's now that you can represent some conditional distributions that are impossible to represent classically. And there are also other distributed problems like consensus where we think quantum resources might be useful. Yeah, that's all I have. Thank you for your time. Happy to take any questions.
Yeah, thank you, Dar. That's great. I mean, great presentation. We noticed that some of your application, or most of them, they rely on the quantum memory. Do you have any idea, estimation, what type of the storage, or how long you need to keep the coherence time to get those applications useful, really?
Yeah, so that's a great question. So I would say some cryptographic type applications that rely on no cloning, right? They only require sort of very simple quantum states that don't require long-term memory. However, some of the examples that I mentioned here, for example, these communication advantages, they require preparation of very complex states. the basic source of the advantage here is you're really using your full Hilbert space to encode your sort of classical data. And this is it's sort of beyond the capabilities of the devices we have today. And you need to sort of keep, to at least prepare this complicated state and kind of keep whatever kind of partial state you have in memory up until you kind of finish preparing this state that you care about. And then once you do that, you might also have to perform a pretty complicated measurement. But at least for some of these problems, a problem like, say, inference with these graph networks, in principle, once you prepare the state, all you need to do is perform a measurement. Like there's no, say, like complicated algorithm you have to run that might require storage for a very long time. But I do think it's interesting to think of like more efficient constructions, and specifically with these consumable data examples. We suspect that some of them can also be achieved with efficient circuits, even though it's something that we sort of hope to study in the future, but haven't gotten around to it yet.
Okay, thanks, Dar. Thank you again for your presentation. And thanks.
Sure.
I know that your time zone this week is not very favorable. And thanks for joining us.
Oh, all good.
And with that,
Sure.
we are moving to our next speaker from IonQ, Aaron Jagannathan. Aaron is basically is the chief engineer responsible for distributed quantum computing and networking in IonQ. He has many senior roles in Microsoft, Xerox, and Duke University, and he holds a PhD in physics and also from Duke University. With that, I will hand it over to you, Aaron. The floor is yours.
Thank you very much, Reza. Are you able to see my screen?
Yeah, we can see your screen and we can hear you. You are good to go.
Thank you very much. So I'm Arun Jagannathan. I'm the Chief Engineer for Networking Products at IonQ. So today I'm going to give you a simple example of what it takes to run a DQC algorithm on a trap-down system. To begin with, this is our vision in terms of an ecosystem that we want to build at IonQ, where multiple quantum devices are connected through a central hub, which includes a switch and also a software-based reconfigurable stack. Today, we are going to focus on the quantum computing nodes that are interconnected, and they are either interconnected at short distances without a transducer at their native wavelengths, or they can be interconnected at long distances using a transducer, which converts the native wavelengths to everyday telecom wavelengths. And recently we made this announcement where we converted barium wavelengths to telecom wavelengths. Our transducers are wavelength agnostic. In other words, any modality, any qubit modality in the visible range can be converted into telecom wavelengths. So I would like to thank Reza for actually defining this discussion in terms of control software and compiler. That distinction is very critical because the control software that drives this interconnection and the distributed quantum computing historically has not been given due credit. And those are all classical backbone that drives this. And this is something that I want to talk to you about today. And the way I'm going to talk about this is I'm going to say, well, how do you prepare a system to execute a circuit? During the preparation stage, the control software is extremely critical. Once the system is ready to go to execute in a circuit, then the compiler stack becomes extremely critical. So if I have to connect to quantum computing nodes, and I'm going to make it very simple, just two quantum computing nodes, no quantum error correction, and last talk was excellent talking about memory nodes. We did announce in our roadmap that we are going to build memory nodes to boost the rates. I'm going to keep it out of this talk. So a simple system, what does it take in terms of control software and compiler? That's the theme of this talk. So if I have to connect two quantum computing nodes, the first step is you generate a photon from each of those nodes. You excite, here you see QPU1 and QPU2. You excite the network qubit that generates a photon. You send those photons to a Bell state analyzer, and you check for Bell state pairs. Once you identify that there is a Bell state pair, you go and execute distributed quantum computing algorithms, because now you have established an interconnection between the two systems. How do you generate a photon? You generate a photon by exciting the qubit with an excitation pulse. For barium, as an example, this is going to be a 650 nanometer laser beam that excites it from the D3 half state to the P half state. And so once you excite them, you can excite them at a very high rate, at a megahertz rate, but not every attempt is going to give you an entangled state. You're not going to generate a photon which is entangled to the ion. So you keep attempting, you keep attempting, and then you wait for an entangled photon that's entangled with the qubit. And as you do this, as you excite this, each excitation is going to heat the ion due to the spontaneous scattering, which means that after a few attempts, and that few attempts depends upon the qubit species. For barium, it might be different. For strontium, it might be different. After a few attempts, you go back and you start cooling the ions. So I want to talk about the lower stack, the bare metal stack. Why am I talking about cooling? Because this is where, when you do a distributed quantum computing network, as you attempt to generate entanglement, and then you go back to cooling, this synchronization has to happen across multiple QPUs. On a single node, it's a simple problem. On multiple nodes, it's a complex problem. We cannot afford to lose time. That is why I keep referring this to a bare metal stack, because you don't even have to have an OS on your RPU stack. All you need to make sure is the lowest latency that you can achieve while executing this. So on a 2 QPU node, you have this full box where you have this loop backing, cooling, and then again attempting entanglement. You need to have 2 of those executed in synchronization across 2 nodes. So the lower stack is in constant communication. You can use an architecture where there's a primary QPU node and a secondary QPU node. They're constantly talking and making sure that they are executing this operation in synchronization, because you don't want attempts in one QPU where the other QPU is actually cooling. Right, and why is it that critical? And this comes back to, I'm going to refer to the Oxford demonstration, where when they demonstrated ion entanglement in 2020, and they reached a world record at that time of 182 hertz, average rate of 182 hertz. But that's just entangling 2 qubits. And recently they published a paper in 2025 that is in Nature, where they actually started to run an algorithm. When you run an algorithm, you need high fidelity. And when you need high fidelity, the qubits cannot be hot. Before they went back to cooling phase more often than their 2020 paper that dropped their rate by 10x. That's 9.7 hertz of average rate. And this is why distributed quantum computing, when we do the actual quantum computing part of the distributed quantum computing, it's a huge challenge. But I'm going to show you how we solve that challenge at IonQ. So we saw how to generate photons, how to send them through the Bell state pair. And here is a high-level architecture. We have load zones. Once we load the ions, we shuttle them to the compute zone, and then we shuttle them back to an interconnect zone. The ions in the interconnect zone are the network qubits, which can be excited to generate the photons. They can be shuttled back and forth. And during these stages, the phase information has to be preserved. This is another requirement, a fundamental requirement on the lower stack. The lower stack constantly monitors the rate and ensures that the phase is intact as we shuttle back and forth. And when we put all these components together in the last few slides, you have separate QPU nodes, and they have their separate chips. And you generate photons, you send them to the Bell state analyzer. And here I'm identifying what those boxes and the circles mean. You have data ions that actually does the computation. You have coolant ions that sympathetically cool the ions. And you have 2 qubits on the interconnect zone. One generates a photon. As soon as you generate the photon, depending upon the T2 star, the coherence time of that qubit, you might have to swap it to a memory qubit for longer coherence times. because the qubit that you use to generate the photons, which are the networking qubit, may not be the best candidate to actually do the computation. So there might be multiple species. As in the case of Oxford, it might be even multiple ions. So they use calcium and strontium. How do we execute an algorithm? How do we go from there? So initially we do a Bell state measurement. After we do a Bell state measurement, we do a swap to the memory qubit. That's the one that is shown in red. Blue is the network qubit. And once we do that, we shuttle and then we execute an algorithm. So I'm going to show you a video because the previous 12 slides are just cartoon blocks. And this is the first time in my, to the best of my knowledge, that we are demonstrating a dedicated compute stack as well as a network stack in a single chip. We did make this announcement during our analyst day call. And before I show you the video, I just want to highlight one thing. The word distributed quantum computing is a loaded word. You have distributed quantum computing. So far, academic demonstrations where people claim that they have achieved world records are on the distributed quantum entanglement part, not on the computing part. Because you can achieve high rates, and over-indexing on the high rates when you define an architecture is not the best path forward. Because the architecture does not only have to take rates into consideration, but it also has to enable computing. So the previous demonstrations at Duke and at Oxford has a max of 3 qubits. So here I'm going to show you a video where you have a dedicated compute stack, which is a chain of ions, which IonQ has mastered over the past decade. And you are also going to see a network stack, which is 2 qubits, a interconnect qubit or a network qubit and a memory qubit. As I run this, I will show you, you can see that the compute zone gets split with a dedicated network zone. So the 2 qubits that you see on the left is your network qubits. The 8 that you see on the right is your compute qubits. There is no limitation there is no fundamental limitation in the number of qubits that we can put on the compute stack. We can put 35 qubits or 100 qubits. This is just a simple demo. And once again, I want to highlight that all this is possible because the lower stack is working flawlessly. Because as we shuttle, they can explode, but we are able to achieve this without any instabilities in our system, in our chip. So this is a single chip in one node. Having shown that, let me show a simple example. So what can I do with it? So I have that, and how do I run a simple circuit? As an example, I'm going to show a BQC algorithm. So traditionally what we do is we use a submit circuits over the cloud, and the quantum computers which are connected to the cloud runs the circuits. The problem with this model is that it is not secure because the quantum computer knows what circuits that the users are running. That brings us to the blind quantum computing regime, where you have a client and a server. Client submits a circuit. Server executes a circuit without knowing any knowledge of what circuit the client is trying to execute. After the server executes a circuit, it sends back classical signals back to the client so that the client can do post-processing and get their results. As a simple example, I'm going to talk about a case study of a quantum comparator circuit. Here, Alice is the client, Bob is the server. Alice and Bob prepare their own quantum state. Alice encrypts her circuit and then sends it to Bob. Bob then does a comparator blindly and then sends it back to Alice. Alice gets to decrypt the results and get the answers that she wants. How does it look like in a functional circuit block diagram? First step, you have a client and a server. This is a 2 QP node system, so you need to generate a remote Bell state pair. Once you do that, then you then the client and the server, they both do a state trap. After they do that, Alice encrypts her state, teleports that state to Bob. And here is a circuit diagram, a high-level circuit diagram of a teleportation gate. It's basically a local C0 gate. You can see the state A. Let's say that's the state of the Alice. She does a local C0, and then she does a Hadamat. After the local C0, she makes a measurement. Based on the results of the measurement, Bob executes an X gate. If the measurement, he either executes an X gate or he will skip that X gate. Similarly, after Hadamat, Alice measures the state, and based on that measurement, Bob executes a Z gate or not. So if I double click that, this is how the circuit looks like. You have Alice Bob. First step, you create the bell state. Then after which Alice does a state prep. It can be anything. So those blocks there are just, does not mean anything. We can create the state in any thing we want. After which Alice does an encryption. After she encrypts, she does a teleportation. As you can see, there are 8 qubits, and I chose 8 for a reason, because that is consistent with the video that I showed the audience. And so she does a teleportation, which is a local C0 and a Hadamat. Based on those measurements, Bob executes his side of the circuit. And once that is done, Bob executes a local circuit. That's the final step. Once Bob executes the local circuit, he sends back Alice to just plain old school classical comms, the results. Alice on her side, which I'm not going to discuss, is going to do an XOR operation that is all classical. And she will know whether her 4 qubits, how does the 4 qubits compare to Bob's? Due to the lack of time, I'm just going to skip to the final result. So this is basically a simulation where Alice compares the state, her qubit state with Bob's qubit state, and this is how it should look like in theory if they are the same. So that's the theory. The dashed line is the theory, and the error bars that you see with dotted dots are your simulation. So we put in what is the decoherence time, what are the local gate fidelities, the swap gate fidelities that we currently have in our system. If we dial that in, we can see the results that are very well aligned with the theory. The red line that you see is Bob trying to be a bad actor and figure out what is Alice sending, what does Alice want to do. And you can clearly see that that's a massive failure. Even if we increase the noise in the system, Bob still fails. That's what makes it blind. And the underlying theme here is, with our current architecture, the noise is in a current system, not the system of next generation. We can actually do blind quantum computing and achieve results where both Alice and Bob are, where Alice is definitely going to be happy. Right. With that, I will stop.
Thank you, Aaron. That was a great presentation. We have one or two questions that I would like to ask you now, and then we can leave the rest for the panel. The one question is that seems that your architecture is using 3 types of ions, the communication, computation, and one for cooling down. So what is the ratio between these different type of the ions, basically?
So that's a great question. So the ratio is something that is specific to the use case. So we can have what we call as a entanglement factory, where there can be multiple bell state pairs for a single compute stack. And then we can also do distillation, where we can get high fidelity bell state pairs. So it is really dependent on the use case. And as we get more complex, there will be multiple bell state pairs associated with a single compute stack.
Okay, great. No, thank you. And another question is that, is there any compiler developed for any of this that you explained? Yes.
Right. Yeah, absolutely. The one thing that I over-indexed on the importance of the lower stack, and I didn't index enough on the compiler. So when I showed the circuit, that's the point of showing the circuit. So when the most important point is Alice measures something, and based on that measurement, Bob has to execute a gate, and that is all compiler heavy. And we have seen that, and when Oxford demonstrated, they hacked something in Arctic, which is so. It's very compiler heavy, and compiler is very important while executing those kind of circuits in a distributed way. Yeah.
Okay, thank you very much. We see you in the panel. Let's move on to our next speaker. Our next speaker is from NVIDIA, Yuri Alexeyev. Yuri is a senior quantum algorithm engineer in NVIDIA and also senior member of IEEE. He is one of the veterans of the quantum computing. He has done many pioneering work on the quantum computing algorithms, error correction, mitigation techniques, and simulation, and also design of the hybrid quantum classical algorithms. So he has a large number of the publication and patents. With that, I will, Yuri, floor is yours.
Thank you very much, Reza. All right. Yes, my name is Yuri Alexeyev. I'm a senior quantum algorithm engineer from NVIDIA Corporation, and here's my presentation. Oops, there is some technical issue. I cannot progress the presentation. You cannot actually. It was just slow. Okay. So first of all, NVIDIA does not build quantum computers. So that's basically our message. What we do, we enable this technology. We build the tools. So, for example, NVIDIA supercomputers, we integrate quantum computers, existing quantum computers that built by vendors, as a coprocessors. And NVIDIA solutions de-risk the quantum industry by being agnostic to the different QPU modalities. We develop hybrid applications that need both GPUs and QPUs. At the same time, we also develop CUDA-Q software framework that allows you seamless applications of programming with accelerated quantum supercomputers. Okay, so this is a high-level drawing of this supercomputer. Obviously, this is very high level. So, as you can see, it very much resembles the existing HPC infrastructure. So you can see on the top, you have AI superchips. These are basically kind of like modern HPC racks. You can see they are connected by classical interconnect. And each of these rack connected to QPU via quantum controller via low latency quantum classical interconnect. And QPUs eventually are going to be connected by quantum interconnect. Next slide. To realize this vision, what Jensen announced at the spring at the GTC meeting, that there's going to be an NVIDIA Accelerated Quantum Research Center called NVQC, located both in Massachusetts. It will feature this Grace Blackwell 200 NVL72 pods. So you can see it's right in the middle, will be 8 of them, connected to QPUs located outside. We partner with hardware partners. You can see at the bottom. We have 5 partners. That will be Qiera, Quantum Machines, Quantinuum, Harvard Quantum Initiative, and QCOS. And the goal with center is to research to enable quantum accelerated supercomputing. I want to say a few words about Grace Blackwell that is going to be used for this machine, because it's actually very interesting, kind of like it's a marvel of technology. The interesting feature that is that it has, first of all, it has a lot of memory, and For example, if you look at the bottom, it has a CPU memory. It has about 18 terabytes, 17 terabytes of aggregated CPU memory, and it will have 13 terabytes of aggregated GPU memory. And since it's DGX system, it allows us to set up this as one continuous shared memory bank. So the total aggregated amount of memory is going to be close to 30 terabytes, and this is just on one pod, super pod. That actually is kind of like opens up to very interesting possibilities because it allows us to run very large scale simulations. First of all, in terms of like state, if you just decide to do state vector simulations, right, it would be over 40 qubits. If you want to do AI for quantum, which is our favorite, it allows you to run very large LLM as well. And you can see in terms of flops, it's also allows to maximum, it allows to do like massive crunching of numbers. Compared to the previous generation of GPU, which is Hopper, you can see it's actually much faster. It's much faster in terms of inference, about 30x, for training it's 4x, and very energy efficient, 5x, and also for data processing. But what about quantum applications on the system? These are just some preliminary benchmarks that we run on this NVL system, and this is a NVL system compared to the state of the art of a CPU system. This is multi-socket CPU system, and you can see that some of these applications. So, for example, Quantum on the left, Quantum simulations with state vector simulations. Most cases with, and you can see you cannot expect a speed up compared to CPU on many thousands of times. And that's basically, it's a kind of a general kind of like expectation as you move to CPU system to our kind of like state of art GPU systems. That's actual multi-x or multi-thousands x speed up. Also, as I mentioned before, for this accelerated quantum computing system, we are going to integrate QPUs. And the question is how it's going to be done. So the key feature is going to be that we need to have a tight integration of quantum QPUs with GPUs. Also, we are qubit agnostic, so we need to support different qubit modalities. The latency here is going to be key. It needs to be super low. One of the reasons why it's super low, because some of the first applications, the target first applications are going to be quantum error correction, calibration, and some hybrid algorithms. And for example, quantum error correction in particular, this requires very low latency. And our reference system that I showed here system, and our partner is was done with quantum machines. So, and typical latencies here, you can see it's if you do it over web API, it's seconds. Also over Ethernet, it's microseconds. If you do it over DGX quantum system, it was demonstrated that the whole round trip going from QPU all the way to the GPU and back, including decoding time, it takes about 4 microseconds. It's pretty long. The reason why it's taking so long time is because it's just a lot of hops, right? Because it needs to go through from QPU to a controller. From controller, it goes to PCI Express. From PCI Express, it goes to CPU. From CPU, goes to GPU. From GPU, and after it goes back. So you can see there are a lot of hubs, and each hub adds some latency, and it's kind of like adds up at the end. And we are looking at ways how to improve this technology. Will be more announcement coming in this area. In terms of programming, I want to take this opportunity to talk about CUDA-Q. This is our platform for accelerated quantum computing. What are the key features? It's a Python, C++, supports both languages. It's a GPU agnostic. That's a general message for the tools that we develop. It's GPU accelerated simulations, so it is actually very much optimized to run on NVIDIA GPUs using CUDA. It does have this fully kernel systems support, kind of like with some similarity to CUDA here. Supports quantum error correction hardware development, and this is for this GX quantum reference architecture that I just mentioned before. We also developed CUDA QX and the AI libraries. This is kind of like also our vision that as we move forward, we're going to develop more and more these libraries, and hopefully people are going to switch and going to more use of these libraries and make it easier in terms of programming with quantum devices. For comprehensive educational tools, we have a CUDA Q academics curriculum developed. It's still under development. So this is a high level of our quantum supercomputing platform. So you can see it has a Python bindings on the right side. The key feature here is that it supports intermediate representations, MLIR, with LLVM. You can see it lowers to a low level to quantum intermediate representatives. And on the bottom here, you can see it goes all the way to physical QPU or simulators. So this is an example how CUDA Q looks like. So you can see the difference compared to our way, kind of like how it's done programming for by ours, is that by using our languages, is that we have a concept of a kernel, and that's a key concept. When you write a program here, you need from the start decide which part of your code is going to run classically, and which part is going to run essentially on a QPU, which part will run on GPU or CPU, and that's all done through these kernels. And so you can see it's done kernel here, and after that we also set the target here. This is NVIDIA, that means that it will run on a GPU, and this is basically the place that it's going to run on a simulator here. When I looked at the presentations here, there's a lot of focus on distributed quantum computing. The good news is that the key feature of CUDA Q is that from the start it was designed to support multiple QPUs. That's a key feature of QPU. So we have this QPU model. So this is Hamiltonian simulations. So it's a kind of like one way how you can simulate this by grouping with poly operators, and there are a couple ways how it can be done. So, but first of all, you can see on the left side, you can see your target. So you say basically where you want to run, and this you can MP QPU. So let's give away what you want to run on distributed mode. And after that, so this is expectation value simulation. And you can see here you have different ways how you can run it. You can run it single node, single GPU, for example. So that's one way to do it. Or you can run it, for example, single node, multi-GPU. So you can see it's done from this parallel thread. Or you can be done with, for example, multi-node or multi-GPU. You support all these different modes. At the same time, we also support asynchronous calculations. So this is an example how it's done. Both observables and samples distributed and expectations can be done using asynchronous state. I mentioned that in terms of parallelism, we support kind of like multiple QPU, and we scale multiple GPUs. All of that kind of like supported. In terms of simulators and QPU backends, you can see we support a large variety of simulators, and this list is growing. At the same time, also we support pretty much all popular QPU vendors, and also the list is also growing. You can find more on this slide. We do have, I will want to briefly mention, we do have a few applications. So this is where our work done with HPU, where we have done distributed quantum computing adaptive circuit knitting. So you can see here on the left side, we have this tensor network. And what we have done, we convert this to this, we cut this, you can see this using, it was, first of all, we computed von Neumann entropy and found the sites of lowest entropy. And that was gives like a sign where it makes sense to cut this tensor network with actually MPS and MPS train. And after that, when we cut this, we basically we basically simulated that, after converted to circuits, and after that we assembled back. And so this is one example of the project. We also want to highlight this paper that we published with HP. It's called How to Build a Quantum Supercomputer. It's on the bottom. Another project underway with Oak Ridge National Lab, where we use CUDA-Q for distributed QA for solving materials and science problems. So you can see on the right side, we took this large QUBE problem, split it to sub-QUBE problems. Here you can see here. And after that, we run QA simulations, found solutions, and after that, found the overall optimal solution. Earlier results show that we have a massive speed up over frontier. Okay, I have a very little time left. So we're also very much interested in AI for quantum computing. I'm going to skip a slide, and thank you very much for your time.
Thank you, Yuri. Great presentation. Given the time, I have only one quick question to ask you. There's a question from audience that is for your GPU connection with the QPUs, do you envisage a specialized connectivity, or what are the requirements for the connectivity to connect these two together?
I need to know more context here. The connectivity of what and what is the application here?
So because you, I guess we can ask further and elaborate on the slide, but the question was that because you mentioned about the latency and problem of latency on running on GPUs, and also on the, I guess the communication become an important bottleneck. Do we need a specialized network for that, or we can use the existing classical network?
So question is like which link to use. In terms of quantum machine learning, we use PCI Express 5. PCI Express 5 is nice, but it does not provide the best, actually. We actually also considering other type of networks as well for lowest. So we certainly looking into also alternatives.
Okay. Thank you very much, Yuri. I will see you in the panel for the rest of the question. We're moving on to our next speaker, which is Inder Monga. He is the Executive Director in EastNet and Department of Energy. Inder is the Director of Scientific Networking Division at Lawrence Berkeley National Laboratory, and also Executive Director of Energy Science Network, EastNet, the Department of Energy High Performance Network User Facility. He's running basically a large network that optimized for large scale science. He has a portfolio of the very high impact research, publication and patent and so on. With that, I leave it the floor to Inder to start his presentation. Inder, the floor is yours.
Thank you. Unmuted myself. So I'm going to talk about some of the control level work that we're doing in this project called QuantNet, which is a 5-year funded QuantNet project from DOE. Now, I'm very grateful to a lot of speakers today that have set up the problem, and I think Arun just couple of presentations ago talked about how important but ignored this control problem is. So I'm going to talk about that. Now, I think I'm going to compare the stuff that we are all doing to abstraction. Basically, we are trying to abstract the complexity of the physics and the hardware that we are building. Similarly, in classical internet, you don't realize it today when you're spending 100 gigabits or 400 gigabits per second. The internet hardware in the 70s was unreliable physical media, and there was a steep attenuation in fiber, which has been solved. And there were things called packet collisions, and that's why you had protocols like CSMA, CD that had to be solved. So the control abstractions that allowed the internet to scale was the TCP/IP, a reliable protocol that hid the physical complexity and errors due to packet drops, congestion, and other things that were happening at the network over that time. I do remember there being, low bitrate modems that we were using that was considered the internet in the early 90s. Now, the internet scaled because of these software abstractions, and we now have a similar challenge with quantum internet. So we have, noisy, delicate quantum devices right now. We talked about sensitive qubits that are prone to decoherence. We do not have a good, reliable memory. And there are a lot of complex analog control challenges and fiber loss when it comes to sending single qubits on fiber. So I think we are the critical missing piece that all of us are trying to solve in this, all the way from compilers down to control software, is the quantum control stack, a reliable programmable layer for managing these quantum resources that are currently at this stage not that great, and we hope that it'll improve. So the conjecture that we have, or the hypothesis that we've been working towards, is the quantum networks will scale only with powerful software abstractions, obviously combined with rapid hardware improvements that many of the companies that I've presented have been working on. So one of our solution, and this is only one of many abstractions that are needed, is the two-level control framework that I will focus my presentation on. Now, before I do that, I'll give you an introduction to the project and some of the requirements that led us to this design. So the QuantNet testbed, or the QuantNet project, is a 5-year project. It's a collaboration between Lawrence Berkeley National Lab, UC Berkeley, Caltech, and University of Innsbruck. And the goal is to build a 3-node distributed quantum networking testbed at Berkeley. And in addition, to architect the scalable quantum network protocols, the control and the monitoring to that kind of envelops and enables this distributed quantum computing testbed. The following is the research team. In interest of time, I will move forward. The 4 areas that the QuantNet project focuses on is to build repeater-friendly ion-trap quantum computing nodes, the silicon color centers, and trying to see if hybrid entanglement is possible, and single photon generation there. Quantum frequency conversion technology, so we can send these qubits at telecom frequencies over longer distances in the fiber, and building a scalable quantum network architecture, control, and management plane. So all of my talk will be focused on the bottom left-hand corner on the scalable quantum network architecture. So before we go deeper into detail, just want to give you a model. Like for any kind of design or software design, you need a model. So our model is their quantum nodes. This include both classical and quantum functions, because you need both of that in order for that node to work, or at least from a distributed quantum computing perspective. Quantum repeaters that don't exist now, but could in the future. The Bell state measurement nodes that are needed to establish entanglement, and quantum channels, which could be fiber-based channels, and optical switches in order to interconnect multiple nodes together. This is something that you have seen. Now, all of this is controlled by a more centralized controller for the kind of scales of quantum data center or metro area that we're looking. This kind of an architecture scales well for that. Now, if you think of layers, we can also look at it in an equivalent of the internet, OSI 7-layer architecture. The physical layer is actually, the photons moving on fiber. The link layer is where entanglement generation happens and purification happens. When you think of the network layer, it is routing and swapping in order to go longer distances, and the end-to-end transport layer, which actually interfaces with quantum applications in order to get a distributed computation done. So this is a proposed architecture. I think there are many people with different approaches, and we hope to get to a standardized way of talking about this in the near future. Now, when we wanted to design a quantum control plane, we thought of what were our goals. So first goal was to manage entanglement, generation, distribution, and storage, which is how to do that most efficiently. So we needed the key requirements was high rate, high fidelity, entanglement generation, and managing both quantum and classical channels. We wanted to synchronize these two, not just all in the same lab with the same lasers. We wanted to have distributed operations that are synchronized. Also to make sure, because in this NISQ era, there are so many errors, we wanted to maximize the chances of successful entanglement. So that is why synchronous operations was something that was important at this time. We wanted to automate the calibration. So it is, as anybody that has built hardware knows that both the node and the link may fall out of calibration, and that maximizes errors. So in order to minimize avoidable errors, we wanted active monitoring of the link and the nodes, and to automate the node and link calibration. So that was part of what we wanted the control plane to do. We wanted to support hard real-time constraints from nanoseconds to microseconds as needed. And for that, we needed time and frequency synchronization, as well as real-time signal and message processing within the nodes. And then I think, as Vijay said, we want to manage this whole thing as a system. So we wanted an efficient, extensible, robust, and reliable control plane, even if you don't have that software here, but the architecture needed to enable that future. So with that, we made a certain design choices. So if you take the goals, the 5 goals that I talked about, and you map it to our design choices. So we went with the logically centralized control in order to do the orchestration and to help with the quantum and the classical channel management and entanglement generation, distribution, and storage. We supported synchronous time slot scheduling to meet goal 2 and 3 about synchronization, and also to handle automation of calibration, which happens on the same links as where the entanglement distribution is happening. We wanted to support real-time control, so we had dedicated channels for real-time communication, and time-critical functions ran on dedicated real-time control systems, which is goal 4, and an open plugin framework that allows these abstractions to be defined, model-based software to be developed, and for the software to be reliable and for it to scale. So with that, I'm going to dive deeper into the tool-level framework. So the tool-level framework is node-wide real-time control. So every node has a real-time control functions, time-critical functions that are defined in FPGAs and that can happen at hard real-time constraints. They mean qubit control, gate operations, node calibrations, and a network-wide non-real-time control to do resource management and to do the scheduling, global scheduling that we need in order for the entanglement generation to happen. Now, in each node, we have our own version of the node OS. I think you heard about from Delft this morning, and each of that is controlled by this ARTIC-based quantum device. So we have a different design for the Q nodes and the BSM nodes that you can read, and there are minor differences between those two that you can read on the slide. And now we have a global scheduler. What the global scheduler does is basically distribute this whole operation in fixed interval time slots that run continuously, and it schedules when certain operations happen in certain slots. Now, this is something that you are familiar with. I don't know how many of you are available, have heard of Sonnet. It is a very similar kind of design, not the same, but it allows for global scheduling and local operations. And that's kind of what our global scheduler looks like. If you want to think of a remote ion-to-ion entanglement process, the right graphic kind of simulates the scheduling from a global perspective, what it can do, the different operations, and then how it communicates to each nodes, which then reserve their local schedules and on the node so that they can accomplish this. Now, assuming that there are multiple nodes in a network and not just two, these kind of synchronization is very critical when you have multiple nodes talking to each other, which is quite possible in a data center environment. Now, this is just not talk or a theoretical design or a paper, but they actually implemented it on the quantum testbed, and we demonstrated that at OFC this year and at multiple times as people have visited the lab. So I'm going to talk about the 4 demonstrations and give you kind of actual graphs of what happened there. So what you see on the left-hand side is the topology and the system design. And this is distributed across 2 different labs with a 5-kilometer fiber distance. Now, this is our talking about link calibration. So the server can schedule link calibration when it detects it out of calibration. And you can say it can go from the left-hand side, polarization, variability, the fidelity out to the right-hand side. And that happens through automated link calibration in the testbed. From a node calibration, we want to make sure that the laser power and the frequencies are accurate. We can do a scan, choose the right frequency and the power levels, and make changes to optimize that. That happens through the sequence that you see defined above, the 500 microsecond sequence with 1 microsecond, reset, excite, detect sequences to get the scans and adjust this. And this node calibration also happens automatically through software control. Now, once you have done the link calibration and the node calibration, what you can see on the control screen, on the management screen, is that the nodes are put in the ready state. Now, a user can request a single photon, and this user we simulated by a human being. It was through a human click on an interface, but it can be an API that interfaces with a compiled software that has been running on a quantum computer. That is quite possible, and that is the next step we are projecting towards. So you can, someone can request a single photon. The quantum network server schedules the time slots for that single photon generation to happen, and what you see is the time graph of the single photon being generated. On the right-hand side, you see the process that it takes to generate the single photon from an ion, and all of those steps are automated in the software stack. And the last one is Bell state measurement, where you can request a Bell state measurement on single photons or photons that have been generated, and you can launch the control sequences for that. Now, this was not an actual ion-ion entanglement example, but this BSM was with weak light, but it shows how we can automate, measure, and graph these phase states that you see psi plus and psi minus on the right-hand side. So the takeaways I will say is that the 2-level control framework and schedule are not abstract concepts. They're implemented, deployed, and evaluated. They're not only designed for the quantum testbed, so the software is something that is available, and we can support different types of quantum networks. That's why we have developed it with the hardware abstraction layer and all of that to incorporate different testbeds. The abstractions and the models we used can be standardized. We are open to engage in normalizing the primitives as we see other people walking the same path. We are doing active development towards those distributed quantum computing goals, and we are ready to evolve our software stack to support distributed testbeds. So if you have one that you would like to use our software, please reach out to me. I just want to say I was happy that this work that we did was awarded the Best Paper Award around 3 or 4 weeks ago at the IEEE Quantum Week on the 2-level quantum framework. And I would welcome you to go to the website and check out all the different work that we have done. Thank you.
Okay, thank you in the great presentation. One question is, what is the purpose of the optical switch in the edge of your network?
The purpose is so that we can do quantum across multiple nodes. I think it is critical. Now, if you only have nodes, you don't need to add an optical switch in the middle, but we want to have a multi-node architecture like in a data center, and I think optical switch will be critical for that.
Okay, have you connected your network with any quantum computing or quantum memory module? I mean, hardware reality.
So we are using iron traps as the two edges, which can support computing. I think we are on the way there because we can do computing and networking using the same node.
And then the final question, then we can go to panel, is comment about the synchronization and how did you achieve the synchronization across multiple node instance?
I think for the purposes of the slots, we used we didn't have to go to White Rabbit, but we needed frequency stabilization at a high level, and we use ULE cavities in order to accomplish that. We used a dedicated fiber to accomplish that across the two different labs.
Thank you, Inder. Please stay on the channel, and also if you can stop sharing so we can move on to panel. Now we are entering the last part of the summit, which is a panel. Panel is chaired by Ramona Tompella. He is a Cisco fellow and lead and head the research activity across the Cisco. Ramona, hand over to you.
Thank you, Reza. Wow. That was some series of talks. We've had some amazing talks ranging from error suppression, algorithmic speedups, quantum advantages, to controllers, to iron trapped distributed quantum computing on iron traps, to even GPUs, right? That's all we've touched quite an array of topics in the generic quantum computing as well as distributed quantum computing arena, and we have had some wonderful demonstrations of the compiler and stuff from Cisco as well. So it's been fabulous and power packed. I'm happy to host this session on just basically echoing some of the questions that I think are burning in several of us our minds, as well as some of the folks that have tuned in. We've had a tremendous turnout. More than 500 people have turned in and tuned in for these sessions. So let me start with some very basic questions, right? So I've given a few talks myself on quantum computing, and the audience actually depending on the mixture of audience, right? So I've seen very basic questions around quantum. So I want to start off with something very simple. As quantum computing industry matures, right, as Vijay's keynote actually showed that inflection point, we are seeing a lot of quantum computing announcements. There's quite a few people out there asking whether this quantum computing industry is going to radically replace the existing classical computing industry as we know. It may seem like a very trivial question, but there's a lot of people out there asking this question. Is quantum computing actually going to disrupt classical computing, or is it going to augment classical computing? And this is an open question to anybody who would like to at least shed some light. Please go ahead. If not, I'll point to somebody and maybe hopefully we can get an answer.
But Ramona, just one point. Daniel Lidar, which is our keynote speaker, said that he's joining. Yes, he was going to be late, so maybe you want to repeat the question. That's just
absolutely. So welcome back, Daniel. So the question is around how with the inflection point of quantum computing, right? Like the announcements around and the interest around quantum computing just growing exponentially. I guess the question that is in a lot of people's minds is around whether this is going to fundamentally disrupt classical computing, or is it going to augment classical computing industry? And the question is open to anybody who'd love to chime in and shed some light on this.
Can I answer this? Because this is very much alliance with kind of like what NVIDIA, NVIDIA's vision. So NVIDIA's vision that we certainly will augment each other. And for NVIDIA, quantum computing is just, QPUs in particular, we are basically just another type of accelerator, right? So for example, think about GPUs. For example, GPUs, we did not kill classical computing, right? For example, what we did, we empowered classical computing and enabled new type of science. For example, GPUs, this is what powers modern AI, machine learning. So in the same way, I think this is what will happen with QPUs. That's basically, it's another type of accelerator, a new type of science, a new type of technology. This is what will happen. And that's basically my answer to it.
So I can jump into coming from the classical networking side of business. I think it's like a marriage. I don't think it's going to disrupt. I think it's going to work together. I think you want to see your images and browse the internet, and those are classical bits that still need the classical internet. And with the quantum internet, you will have a whole new range of applications that you didn't have before, and that is going to coexist with the classical internet and the classical network. So I don't think either one is going to disrupt anything. And one of the, I think the fun things is the fiber is the common element for both networks. I mean, both the classical bits and the quantum, the flying quantum bits, which are photons, go over fiber. So I think it is like a marriage rather than a competition or kind of like the image that says when you said one thing is going to kill each other. I don't think that's going to happen.
Okay, thank you. Moving on to the next question. So, this.
Ravana, I think Alex Iskandar wanted to also comment.
Oh yeah, please go ahead, Iskandar. Can't see the.
Thank you. So I think the reason why those questions sometimes being asked is because of lack of communication, probably from the quantum industry, right? So majority of what people see on the media in news are like very flashy headlines, right? And I think that's this event that is organized today, right, and going to be tomorrow, actually a good stage, right, to promote this more like engineering view on this topic, right? So actually tell what is actually happening, right? So people know and do not create these false claims that quantum computing will replace everything else, right? So I absolutely agree with Yuri, what Yuri said. So yeah, that's it. Sorry.
Awesome. Yeah, no, I think with yeah, it might sound like a very basic question, but I just wanted that to get clarified across the board. Now, moving on to the next question, right? So quite a bit of discussion around distributed quantum computing. I guess one question that often pops out is, do we see distributed quantum computing as a necessity, or do we see that as an enabler for a few extra types of algorithms and applications? In other words, can we do a lot with a single quantum processor, or do we absolutely need a distributed quantum computing framework in order for us to target those enterprise grade applications that everybody thinks about? And I think maybe, given Iskandar, you just spoke a little bit, so maybe I'll come to you.
Okay, and it's also always great to point to people, otherwise like shared responsibility never end up
Exactly,
in a good place.
exactly. So now I learned my lesson.
Yeah, so I think like in general, right, with any technology, the holy grail is to do the horizontal scaling, right, which you can tell the distributed computation, right? So in anything, right, in any technology, computing in general, and in theory, we know that useful quantum computation comes with like larger systems, right? And we also know from the experiments from different hardware vendors, right, different labs, that scaling vertically machines is really challenging task, right? So inevitably we should come to distributed quantum computation, because that's the pretty much only way to scale this technology.
Let me take a somewhat contrary view to that. So we know that in order for quantum computing to provide us speedups, we have to generate entanglement across essentially an entire processor. So if you just take n local quantum computers and you connect them, but you don't ensure that they become entangled, you haven't really done much more than just create n classical copies of finite size quantum computers, and that's not going to scale in the sense we want it to scale that is necessary for quantum speedups. So the caveat is, yes, distributed quantum computing is great, but only if you can ensure that entanglement spans the entire network.
That makes sense. That makes a lot of sense. Of course, they need to be. Reza, you have.
Yeah, I mean, I want to say that when we say distributed quantum computing, if for a scale out is, I think there is no question you need distributed quantum computing and networking your quantum processors. In fact, almost all existing vendors that they are moving, they are using the network. Maybe they are very short distance because they are limited to the mode of communication, mode of the qubits, but nevertheless, still they are using the network instructions. I think that the scale is going to increase with the advance of the technology to a larger. Now, therefore, you can say distributed quantum computing is definitely the way that Daniel mentioned, entangling the processor at the short distance is no way to avoid it. Now, the question that is gonna, I think we need to answer is there gonna be a supercomputer that is using the network to scale to a bigger single quantum computer, or is gonna be what today's hyperscaler provide, a cloud platform that you really get a different algorithm and distribute it across that. So that's something that I think is jury out. It's gonna be like that or not. But in terms of building a network to get a bigger processor, definitely is gonna be there. That's my point. Yes.
All I
No,
can
thanks,
say
Reza.
is
Go ahead.
HPC today is not one single computer. It is many processors and GPUs networked together. That is what an HPC is. So I think I understand completely the challenges both in scale up and scale out, and that is the way I would say it. I think both have to happen in parallel, and there are challenges in both those forms. What Daniel said is a challenge that needs to be solved in order for that to really be useful.
Over to you, Arun. You have a point of view.
Right. So distributed quantum computing or not depends on your scaling strategy, right? So there are certain qubit modalities where DQC is not the best path forward for scaling. For modalities where DQC is the best path for scaling, I agree with Daniel that you need to have high fidelity, high rate in order to make sure that it actually scales up. So it depends on the qubit modality. And very briefly answering a previous question, Ramana, I think disruption will happen on specific problem sets. Daniel had a great slide, right? He showed, so it's not going to a global scale disruption, but for specific problems, there will be disruption to classical computing.
No, that makes sense. So Arun, now that I have you here, right? So I guess one question that pops up. Yeah, so you're absolutely right. The distributed quantum computing may not be the best modality for, or best way to really break it up for different types of heterogeneous technologies. For IonQ, I mean, you've talked a little bit about DQC. Do you see that as a viable path forward? Is that the right way to scale out, or your ion trapped systems? Or I mean, what exactly is your roadmap around this?
Yeah, so we did disclose a roadmap a month ago, and we are fully committed towards scaling based on distributed quantum computing. We have other paths to scale as well, but we are fully committed as of today.
And what is the key technology that is like an impediment or a roadblock to actually achieving the scale out of distributed quantum computing in your view?
That's a great question. So it's the balance between fidelity and rate. So sometimes you can get, and this I can go back and refer Oxford's paper, right? So you can get high fidelity, and for high fidelity, you might take a hit on the rate. So how do you balance both? And this is why our recent acquisition of LightSync, where the rate boost will be provided by the memory node. And we hope to maintain the same kind of fidelity that we have on our local gates. So that's our path forward.
So is it fair to say then that it's really now just a matter of just getting there as opposed to some of the technology de-risking that has already happened? Or I mean, is it more of an engineering right now as opposed to this like fundamental challenges that are yet to be solved, for example, in this space?
Right. So the component level de-risking has been done and demonstrated individually. right? We know that the memory nodes are working. We know that the quantum computers are working. We know we can generate entanglement rates. Chris set the record at 250 hertz. So we know the individual components are robust. So there's not a fundamental roadblock. It's the engineering roadblock, as you correctly pointed out.
Gotcha.
As we integrate them, yeah.
As the other quantum, technology provider, IBM, I'm going to come to you, Iskander, to sort of see if you have a contradictory or a complementary viewpoint around this.
Yeah, I will yeah, move to the next one. Yeah, I think I'm good. Yeah, I'm agreed.
Okay, all right. Sorry to put you on the spot, but like I thought it'll be good to see at least from maybe anybody else in the audience in the panel, the fundamental impediments to actually achieving distributed quantum computing. And maybe Reza, you can chime in as well.
I mean, there are obviously hardware problems and software challenges. In spirit of this session software, I would say that the major roadblocker is distributed error corrections. And based on at least the team in Cisco understand, I mean, that's going to be a quite big step change, a distributed error correction compared to what you do monolithic in a single quantum computer. You need to bring a lot of additional dimension to a completely new and novel research or science area. So that's, to me, is the biggest hurdle that needs to be addressed.
Yeah. Roman, I would like
Please
to
go ahead.
add a
Please
point
go
here
ahead.
that I don't think people mentioned it. We can all agree on probably two things. One is that eventually, ultimately, at the end of the game, there will be distributed quantum computing, and that's a necessity. Also, that distribution of entanglement between different units is a hard challenge, hard engineering challenge. So my view, and I'm quite confident about this view, is that on the path there will be single chips, not distributed, single chips or single whatever, neutral atom modalities or ions, that I would put the limit somewhere around 2000 qubits. 1000 still is fair enough. That could be on a single chip with full coherence between them. And then we will reach the real era of heuristics quantum computing. If we look back at the history of classical computing, theoretical computer science taught us a lot about theoretical possibilities. It guided the algorithms, but all industrial algorithms, with no exception, I would say, are all heuristical algorithms in optimization, in machine learning, in AI. Everything is heuristics. Nobody can prove large language models can do the magic that they do theoretically. And with 1000 or 2000 qubits, which are possible without distribution, we will start this era of experimental heuristic algorithms. And I think this will be quite a long time where we will get the advantage from single chips, and only later on we will go on to distributed quantum computing, which is much harder.
Thanks, Yehuda. I think that makes sense. One of the things that I think we talked about, I think Daniel, you mentioned is around error suppression. I mean, we keep hearing about error correction, error mitigation, but error suppression is definitely something that you brought out. I would like to know, in the context of a distributed quantum computing, how does this actually manifest? I mean, is there an equivalent of error suppression in a distributed quantum computing environment?
Absolutely, yes. I mean, so first of all, error suppression is as old as the 1950 Hahn echo experiment. So it certainly predates quantum error correction and mitigation. These techniques, dynamical decoupling and so on, have been around for a very long time, but they've really seen a revival thanks to the efforts of the quantum computing community with many important advances. Now, specifically regarding the distributed case, so I'll just point to work that I did more than 2 decades ago, where we were interested in suppressing quantum noise in optical fibers. And you can do that using dynamical decoupling techniques. They apply beautifully. Essentially, you can use phase shifters and beam splitters to implement error suppression operations. And you can essentially, if you put the optical elements close enough inside the optical fiber or around it, you can show that you can eliminate problems involved in photon transmission, including even absorption, as it turns out. So I definitely think there's going to be a role for these techniques in the same way that they appear in a localized quantum computer. That is, they act sort of as a first layer of defense. Essentially, they remove all the non-Markovian noise. And once you remove the non-Markovian noise, you're left with the Markovian noise. And that is something that error suppression techniques cannot deal with. And that's where you need error correction.
Gotcha. So in other words, what you're saying is there is enough body of work around distributed quantum error suppression, but it can only go so far, and then error correction and error mitigation have to sort of come in to sort of get you the whole way through. In other words,
that's right. But it's also not a good idea to ignore these techniques and just put all the onus on error correction, because then the error correction has to do a much heavier lift, and you get poor performance as a result.
Got it. I think that makes a lot of sense. So is error suppression something that anybody else have considered or looked at in your either software or your hardware implementations? I mean, can anybody else chime in on this, perhaps?
Maybe I'll make a quick note here. It's in terms of quantum error correction, so we are entering this era of partial kind of fault tolerance, and with logical qubits, we are not going to be actually vastly better than physical qubits, right, in terms of fidelity. So, and these techniques what you just Daniel mentioned, right, like error mitigation techniques that we use for physical qubits, right, for NICS computing, I expect them going to be fully applicable, fully still widely used as well, but applied to logical qubits. And that's my expectation. But I have not seen really any debate on this, and it'll be really interesting to know opinion of our people on this panel. What do you think about this?
I think Iskander, you wanted to chime in here, please.
Yeah, I think I agree with Yuri, right? So there's, first of all, there is not going to be like the step function, right, when something like came up, right? So we'll have more like a gradual migration to error correction, right? And error correction will be improving as we move forward, right? It's not that in like 2030 everybody's like achieved error correction and we're like all live happily afterwards. The thing Roman, you asked about the error suppression mitigation techniques, right? The platform used, for example, at IBM Quantum, we're using it in our runtime service, right? We have it. We have dynamical decoupling, which Daniel was talking about, right, as options, right? So we open it to the users to when users submit circuits, right? We do this on the service side to conduct those routines. So yeah, those are viable options right now for current generations of system and moving forward.
Awesome. Any other thoughts before we move on to other topics?
I can give a specific example on the same vein as what Daniel discussed. So when we generate the photons from the network qubit, it has a very finite coherence time. And your clock starts when you generate the photon. So therefore, we do the old school, the spin echo or dynamic decoupling to prolong the T2 star as much as we can, because the communication, very specifically in a distributed way, has to happen approximately 1/10 of the T2 star. So yeah, error suppression we have to do it. That's a basic requirement, and error correction comes next. We cannot live without error suppression.
No, that makes sense. Arun, while I have you here, so I think one question I have is on the transduction that you mentioned from your, matter qubit to a flying qubit, the photonic qubit, right? So what kind of fidelities have you seen in your transduction? What kind of efficiencies have you seen in the transduction process? I mean, is it sufficient for you to, like, for example, really run, a partition, like distributed quantum computing circuit partitioning over, like, let's say hundreds of thousands of gates, or like what types of gate depths can you actually expect with that kind of efficiencies? I guess that's a question.
That's a good question. So it also depends on what rate you start with. And so it's a combination of what rate you start with and what is your efficiency. We will publish our results soon, so we are fine-tuning our results. I won't be able to comment on the fidelity, but we expect efficiencies towards 50% based on our architecture. It will be multi-stage architecture, but we do expect that.
And do you also have like something in the distributed error correction regime that, like, you're going to talk about at some point, or like, is that something that's still work in progress, or can you comment a little bit on that as well?
That's a work in progress. That's a separate dedicated team. That's a work in progress. Yeah.
Okay, thank you. So one other, like, topic that I wanted to touch upon, given we've spent a fair bit of time on distributed quantum computing, is blind quantum computing. I mean, this surfaces every time because, I mean, I think one of the properties of quantum that we all get like sort of very enamored by is this whole no cloning theorem and the advantages of it, right? So blind quantum computing is obviously one of those applications that can benefit a lot, and I think we've heard folks talk about that. But in the classical world, right, this whole privacy preserving computation and all that stuff has seen some success. I mean, secure multi-party computation, there's a bunch of like analogous themes around how we can leverage techniques to sort of preserve privacy and all that stuff, right? So, and we're sort of at the very early stages of quantum computing, and is really blind quantum computing, I thought, is a second order or a third order problem statement. So why are we talking about it now? And is that the right problem to be even thinking about right now? So.
Yeah, from an industry perspective, I don't think this is the main concern of any real enterprise customer now. They are very much concerned on creating the first stack of their algorithms, their first prototypes. At this stage, they are not worried about privacy or confidentiality or proprietary. I don't recall even a single case where this was a main concern, even from relatively, I would say, delicate industries such as banking and so on. So it's, from my perspective, it's kind of down the road and still a research activity.
Gotcha. Any other thoughts around blind quantum computing?
So it depends upon the use case and what type of customers we are talking about. So on the industry side, I would definitely agree with Yehuda that it may not be a flashy problem, but on the secure comms, on the government side, it is a very interesting problem. And if we ask this fundamental question, if I have two quantum computers that are separated by 10 kilometers, what's the problem that you can think about? Is it a scalability problem that you're going to address, or is it going to be something else? The first thing that pops up in an engineer's mind would be blind quantum computing, because it is something that we can do today, like we showed. And even small extremely limited use cases is beneficial to certain customers.
I want to put a slightly different view. Blind quantum computing is necessary, but is good, understand the application, what I want to say, not necessary. But that requires depends on what scheme you develop, but a most scalable one of block caving needs a memory. So if you need a memory, if you solve a memory problem, you open memory and network problem, connecting memory to network, then you open the whole new set of application, which I think blind quantum computing is not the most important one. That's my view. So if you manage to build a memory, I think it makes more sense to do all more interesting application beyond quantum, I mean, separate from quantum computing, classical domain. Let's say telepathy and so on can be achieved easily. So those are, the question is that the challenges are right challenge to address, but is it the right application for those challenges? I am not sure.
Yeah, it sounds like, it's one of those intrinsic properties of quantum that you definitely want to take advantage of, but like, so it's a kind of an application that is sort of like, there to take advantage of something intrinsic, but that's not where like, a customer is seeing as a main pain point, to Yehuda's point, right? I think it's not one. If you poll 100 people, I mean, that's not on the top of their list for sure, I guess. So the, as we march towards like, the last few minutes, so one of the questions, one of my favorite questions, right? So, and feel free to speculate a little bit here, right? How close are we to actually breaking classical cryptography using Shor's algorithm? This is one of those favorite questions that I get asked all the time. And it's fine to put a hand wavy answer, but I would love to at least get a take on this.
I think we lost Ramana. Yeah, I don't know. Cisco TV team, do you have a?
Oops, sorry, I think I lost you guys for a second there.
Okay.
Well, I'm happy to comment on that a little bit. So actually, if you recall, I showed a slide of the state of the art, which is we can factor 21 with 70% probability. And that hasn't moved since actually 2021 is when that paper was published. And we've looked at this problem very carefully in my group to see what can be done with today's processors. And the answer is very little. That paper by Craig Gidney that shows that we can factor a 2048 RSA number in a week with 1 million qubits is encouraging. Of course, it also makes a lot of assumptions, but it's still that is 1 million qubits, 1 million physical qubits, mind you. Okay, not 1 million logical qubits. But that seems like anybody's guess how far out that is. Probably at least 5-10 years. All that said, this is an unclassified panel, and we don't know what is going on behind the scenes, right? So maybe numbers are being factored already. We just don't know about it.
Anybody else with a bold take? I certainly think with distributed quantum computing and the advances we are making in building out a quantum network with distributed quantum error correction and and transduction that Arun talked about and all these things, right? I think all the pieces are there, and these pieces will probably bring the timelines substantially, right, compared to just a pure scale up kind of an approach. So if all these pieces actually do come together in a perfect synchrony, I mean, you are looking at potentially getting to a 10,000 qubit to 100,000 qubit data center ish in about maybe 5 years ish. That sounds very reasonable to me based on all the talks and based on all the advances that people have been showing out. Is that consistent with any other thoughts, or am I the only optimistic person here?
Yeah, maybe I'll add to that. 5 years seems like it's not really hard to put any numbers to that, but looking at vendors, different vendors' roadmaps, they look very aggressive to me, right? What Cuyera, Quantinuum, right? IonQ, IBM, right? So it seems like we will have tens of thousands, maybe even hundreds of thousands of physical qubits, right, in 5 years or so. It's in the roadmap. I don't know if it's going to happen or not, right? So that will put us in the realm of possibilities. But maybe a question for Daniel is that the number of qubits, right, and fidelity is not the only factor here. Another factor here is, of course, is the speed as well. Do you look at actually, is it even feasible? Because assuming that you have lots of qubits, right, and assuming that you have fidelity, but if it takes very long time to execute that, right, it's still not really feasible.
Well, I think the best source we have right now for that, a publicly available source, is again that paper by Craig Gidney, which the timescale for factoring a 2048-bit RSA number is a week with 1 million physical qubits, according to that paper, and that makes heavy use of surface codes and so on. And this is based on, I think, on Google's chip technology, which a week is okay if you're worried about it taking the edge of the universe because of how slow operations are. That's not where we are. But I think the other relevant question here is, does it really matter, given that we've already entered the post-crypto, post-quantum crypto stage, right? And so should we still think of this as the driving killer app? Probably not. I would argue that the real killer app is quantum simulation. That's the low-hanging fruit. That's where we see the quickest progress. If I had to bet on anything, I would say we're going to see the real first impactful result that is kind of a game changer with practical applications coming in the area of quantum simulation, not in factoring.
Actually, on that topic, what would be the next? I mean, molecular simulations is definitely one of the clear applications for quantum. I mean, as even Vijay's keynote talked about how Feynman's quote around how nature is very much quantum and that kind of makes sense, right? So what would be your like let's say top 5 applications, right, that quantum is going to fundamentally impact, apart from, of course, molecular simulations?
Yeah, so simulating quantum chemistry, molecular simulations actually is harder than doing spin systems, because you have to map a system of fermions to qubits, and there's a lot of overhead in doing that. So I would say that simulating the properties of the various magnetic materials is probably where we're going to see the first impact. Not necessarily bosonic systems either, but truly spin systems exhibiting interesting magnetic phenomena, giant magnetoresistance, etc. Discovery of new materials, perhaps in that realm, when you couple quantum simulation with AI, that could be another area.
Any other applications other panelists would love to bring up? Like, what about ML, for example? Yeah, I mean, Daniel mentioned AI, but like AI ML together, of course, is that bound to happen in the next 2, 3, 4 years? I mean, and what would be the exact use cases that could be powered with the help of a quantum computer in that arena?
Actually,
Yeah,
since
Go ahead,
ML is such a heuristic arena, we see already today, and we will see ahead in the future, a lot of quantum-inspired heuristics. So that's one additional place where quantum will have impact, even before the hardware is here.
Makes sense. Iskander, you were saying something.
Yeah, I think at the end of the day, it will still boil down to this algorithmic discoveries, right? How can you efficiently map your problem to the circuitry, right, for digital quantum computers, for example, right? So, and at the end of the day how much effort you can put to the
True. I think that makes
in
sense.
specific areas, right? So right now, like a lot of research is happening, chemistry, right? Molecular simulation, like what quantum computers is good at, simulating nature, right? Like quantum mechanical system, quantum computers should be supposedly good to simulate quantum mechanical systems, right? So that's where a lot of research is happening, a lot of investments going there, right? So a lot of algorithms discovery, right? Experimentation, and this like have this like snowballing effect, right? Optimization, anything related to optimization, because it's like wide variety of impact, right? Those industries looks like they're the best candidates.
To me, I think that's a very fascinating synergy between quantum and AI, right? Of course, there's AI for quantum, which is like what we've heard Yuri talk quite a bit about with GPUs, like assisting in various quantum functions. But I think quantum applications in AI ML are going to be, I think, something that I would be very, at least personally, curious about how it can potentially disrupt the whole AI industry that we're all very excited about and part of. So on that happy note, I think we're at time, and I know Reza will kill me if I go way too much beyond. So I would love to thank all the panelists today for wonderful and insightful discussions and all the beautiful talks. Like I've heard insightful and inspiring talks that I've heard all through the day, and I'm also very, very excited for an entire day tomorrow around how quantum can power classical applications. And I think that's going to be an interesting set of sessions to watch out for. And for all, and I'd also like to thank all the viewers that have tuned in and participated in asking all these wonderful questions to our esteemed panelists and making this like lively. And I'm hoping that the enthusiasm will continue over to the day 2, and see you all tomorrow. And over to you, Reza, for any wrap up.
No, thank you. Thank you for everybody and our audience, and thanks for presenters. We had almost 600 people tune in to watch today. The session would be available, I think, in a few days over the recorded video in Cisco Research website and also in our YouTube channel. So that would be available if you would like to refer your talks or anybody this session today for later on. Please do so. And I hope to see as many as you possible tomorrow. And thanks again for contributing to our summit.